Most food safety professionals I work with across all industries, across all continents, are competent, they are trained and committed. And yet, the same failures keep happening, not because people don't care and not because procedures don't exist, but because the system itself is working exactly as designed. Welcome to Systems Thinking for Food Safety. You will know the answer by understanding the hidden architecture of how food systems actually work. Module 4 today introduces you to systems thinking, not as an abstract, but as a practical lens for understanding why food safety problems persist despite our best efforts. We will learn together, step by step and through applications, how to spot patterns, how to design connections, and how to design feedback loops that determine whether your food system protects or fail your food safety system. This is presented to you by Walball, founder of QHSE360.org. Who this course serves, we design our course in a universal language of food safety. So this course is designed for a broad community across the entire food system, from small farms to multinational corporations, from production floors to boardrooms. We have designed every concept and every example and every tool in this course to make sense for you, whether you are managing a 5 people processing facility or managing a global supply chain. We are serving the primary production and manufacturing sector with our course, and that will include primary farmers and primary producers, food and ingredient manufacturers, multinational food companies, and small processors. We will serve you all with the information here today and the practices and the tool to help you better your system. Also, this course is designed for distribution and services, and that include cold storage and logistics provider, importers and exporters. It's for retailers and for supermarkets, and also is designed for food services and catering chain. Also, this course is designed for professional specialists that include food safety managers and quality assurance team. It's also designed for internal and third-party auditors. This course is designed for food safety consultants also and for technical specialists. Also, the course is designed for governance and oversight. It's, the course is designed for regulatory professionals, for NGO and public health officials, for supply chain managers, risk managers, and for senior leadership teams. The design principle of our course, we made sure that every module must make sense to both a small farm and a global corporation. We speak a universal language of food safety system. So the systems thinking principle that we will learn together today apply whether you are producing 100 unit per day or 100,000 unit per day, because the underlying patterns of how systems behave are the same. Now, let's explore the question that changed everything. If you have studied Module 3, after studying the 5 failure patterns there, you have seen how food safety breaks down. We will touch base on this failure here too in this module. So after doing that, you can ask yourself the following question. Why do these same patterns pair across different companies in different countries, different products, and even different decades? Same patterns. repeat themselves everywhere. The same way food fail in Europe is the same way in Africa, in Asia, and in America. The same recalls, all right? The same crises fall with the same patterns that we studied last time. The answer to that is not about individual failure or bad actors. It is about how food systems are structured and how that structure creates predictable patterns of failure. Now, today, this module will teach you to see that structure. And once you see the structure, you will change the patterns that make food fail everywhere. The same 5 patterns we studied last time. All right? Now, let's first uncover the critical reframing here. From traditional way of fixing the problems, we will move today to understanding the systems. So when the problem happen, we will not just go there to fix, but we will go there to understand. And let's do it together. The traditional way in food safety, when the problem happen, it want to be fixed, right? So the investigation start with what went wrong and who is responsible so that they can fix the problem. But systems thinking ask the following question to start their investigation. What conditions allow this to happen? And how do we change these conditions? Here, the shift in thinking and in approach and investigation is not semantic. It's not just the change of term, but it's fundamental. The shift in approach, deep rooted, to change the paradigm, the way of thinking. And I will demonstrate shortly. Let's see the fundamental difference here from traditional approach and from systems thinking. Let's start with traditional approach for fixing the problem. The investigation will start what went wrong and who is responsible, right? What do you think will be the first step here? Evidently, first is to identify the failure point. Wonderful. Now, let's see in real example the identification of failure point in traditional way. Real world example here in a small dairy farm. So a small artisan cheese producer discovered listeria in their aging room. That's the failure point. So the traditional approach, the failure point is the aging room. What's required there? The deep clean, the aging room, and resume the production. Another example for the identification of failure point in traditional way. In a large manufacturer, a ready-to-eat meat plant finds salmonella in finished product. The traditional approach again to identification of failure point. The failure point is the slicer. That's what they found. Okay, so they sanitize the slicer and release the next batch. Investigated, found it out. The failure point is the slicer. Okay. And the second point in the investigation in a traditional way is to find the person or the process responsible for the failure point. All right. So let's see a traditional way with example. In a restaurant chain, a catering operation has an allergen cross contact incident. The traditional approach here again, they found that the cook didn't follow the allergen protocol during their investigation. So they retrained the cook and document the training. That's the traditional solution. All right. Let me demonstrate with a different company. In a produce packer, a lettuce packer facility ships product with high microbial count. Okay. In the traditional approach here, they found out the wash system operator didn't maintain proper chlorine level. So what they do, they discipline the operator and require supervisor sign off on chlorine log. All right. Now, what would you think will be the third point in traditional approach? It's to implement corrective actions, right? Now, in the implementation of corrective action, let's demonstrate also with two real companies. First, in a bakery, a bakery has mental contamination in bread. So the traditional approach, when they found out it's a metal detector sensitivity need to be adjusted, they did that. Adjust the sensitivity, the real calibrate the detector and verify that it catches the next piece. All right. This is the implementation of corrective action in traditional way. To demonstrate that point with another example, so the beverage manufacturer, a juice company, has malt in product. Okay, so the traditional approach there again is to increase the pasteurization temperature by 2 degrees Fahrenheit, and then they will validate the new temperature and update the HACCP plan. Corrective action is implemented, and then of course move on because the corrective action is documented, the audit finding or the investigation finding is closed, and the production continue. Everyone believes the problem is solved until it happened again 3 months later or any time later or in a different place in the facility with different people. Now that's a traditional way of investigation and applying actions. Let's see the system thinking here. The system approach for we said before, you don't fix the problem, you understand the system first. Okay? So understanding the systems, you start your investigation with the following question. What conditions allow this to happen and how do we change those conditions? All right? This question will lead to the following sequential investigation and solutions. Let's do it together. First, identify the failure pattern. Okay? Now we will demonstrate again with the same companies, but now with a different approach. Same dairy farm, now the system approach will start. The producer will ask the following question as they're starting for the investigation. Is this the first time we have found listeria in the aging room? That will be the leading question for the investigation. And as a result, they discover it's the third time in 18 months, always in the same corner, always after high humidity weather. You see, this is a pattern here, not an isolated event. Now, for identification of the pattern, let's demonstrate with another example. Same large manufacturer. Here, the system approach, the meat plant will ask the following question as the start of the investigation. Do we see salmonella in other locations? As a result, they review environmental monitoring data and discover the slicer tests positive every month. And also, the floor drains test positive, and the forklift wheel test positive. and the door thresholds also test positive. So you see the pattern there. Salmonella is resident in the facility environment, not just on the slicer. All right. So now you see the approach here is to identify the pattern, okay, not the failure point. Now, what do you see in the investigation system approach? The second the second point, the second sequence will be to understand the system conditions that created it using systems thinking. Understand the system's condition that created it. How? Let's demonstrate same examples of the companies that we did in traditional approach. Now, in the same restaurant chain, the system approach will be the catering operation investigations would it start with the question, what conditions exist when these happen? That's how it will lead their investigation. And as a result, they discover that it was a Saturday wedding. So there was a high volume there. Okay. We are talking about the changeover allergen incident. And secondly, they found out that the regular staff called in sick and there was an understaff on the wedding day. So two people that were supposed to come and serve didn't turn up. They were sick. And they found out that too during their investigation when they tried to understand the system conditions, not just the cook didn't follow. Okay. Thirdly, they discovered that the kitchen was running 2 hours behind the schedule. So definitely there was a time pressure also on the cook. Fourth, they discovered that the allergen protocol requires 15 minutes for changeover, but only the cook has 5 minutes available. Okay. Now, the system condition here with this investigation, there was high volume, one, plus understaffing, two, plus time pressure, three, plus infeasible pressure. Okay. All of these come together and it is equal to predictable failure. All right. That's what happened. Now, let's demonstrate with the second example to understand the system conditions that created the problem. The second is let's apply that to the same packer. The system approach here will be the latest facility investigates and start with the following question. What makes maintenance, what makes maintaining chlorine level difficult? Okay, that's how they will start their investigation. So they will discover the following. First, the chlorine demand varies with incoming soil load. So evidently, that's unpredictable. Secondly, automated dosing system frequently malfunctions. So that is unreliable equipment. Thirdly, operators have no real-time feedback on chlorine level. That is delayed information. Fourth, the lab results come back 24 hours later. That means it's too late, correct. Finally, the production pressure means operator can stop line to troubleshoot. So there was conflicting priorities. And you see now the system conditions here means there is a variable demand plus There is unreliable equipment, plus there is a delayed feedback, plus the production pressure. All these came together, and the result, it was inevitable chlorine control failure. So it's not just the operator. Okay. Thirdly, in the system approach, let's go to the third point, which is recognize how these conditions persist across your operations. Okay. Let's apply same companies in traditional approach. Now the same bakery in the system approach here, the bakery will start the investigation by asking, where else do these conditions exist? The metal detector failure. Okay, so as a result, they will find out the following. First, metal detector sensitivity is adjusted frequently. Why is that? Operators they reported false alarms too much at high sensitivity. Then false alarm stop the production. Well, so they do that to avoid the pressure, production pressure. Then supervisors face pressure to maintain throughput. All right, so there is a conflicting goals there, right? Then, so sensitivity gets adjusted down to reduce false alarm. You see the picture here now? These same patterns exist. They found out also this same pattern exists on 3 production lines also. The metal contamination is a symptom in this case, and the system condition is the conflict between detection and detection sensitivity and production pressure. All right. Now, let's demonstrate with demonstrate the same point with a different company with the second company from the same approach in traditional there. Now, the same beverage manufacturer, okay? The system approach here, the juice company will start the investigation by asking what conditions allow mold to survive pasteurization. And then they will start the investigation and they discover the following. First, product temperature varies across the heat exchanger. And evidently, that's a design issue. Secondly, they discovered that cold spot exists where temperature is between 3 to 5 Fahrenheit below target, and that's spatial variation. Then they discovered that temperature probe measures the hottest point, so that's a measurement location bias. And so the system thinks it is achieving pasteurization, but cold spots survive. Now, they check other heat exchangers and find the same design issue across 4 production lines. Raising temperature on one line doesn't fix the system condition in this case. So the design flow persists. The fourth point here is to redesign the system to eliminate those conditions. Now that's systems thinking. It's not to apply corrective actions only on the failure point. Here is to redesign the systems to eliminate those points completely, right? Now let's eliminate all those points one by one. And you can apply the same concepts in your operations immediately, all right? First, in a small dairy farm, the system redesign would be the following. So instead of just cleaning the aging room, they will they will do the following. First, install humidity monitoring with alert, and that will make the conditions visible. Secondly, redesign drainage in the corner, and by doing so, you will eliminate the moisture accumulation. Thirdly, adjust air circulation patterns. By doing so, you change the environmental condition. And finally, implement daily visual inspection of the area to facilitate early detection. So the farm did that, and as a result, no listeria detected in the location for the next 24 months or 2 years. The system condition here have been changed completely. All right, not just deep cleaning in the corner. Now, let's redesign with the large manufacturer, the system redesign. Instead of just sanitizing the slicer, they will do the following. First, implement zone separation with physical barriers, and this for control of the pathways. Secondly, redesign traffic patterns to prevent cross contamination by changing the flow, right? Thirdly, increase environmental monitoring frequency from weekly to daily, and this will give you a faster feedback. Fourthly, establish automatic production halt for any environmental positive. And this is a strong feedback loop. And finally, redesign flow drains to eliminate harbor sites. So you are eliminating completely the niches. The result here, the light manufacturer implemented that, and the result, environmental listeria detection rate dropped from 15% to 2%. All right. And the finished product positive test went to zero for over 3 years. All right. Let's redesign the other companies now. Okay. The restaurant chain, instead of just uh, retrain the cook as they did in the traditional way, now the system redesign, they will do the following. First, redesign allergen changeover to take 8 minutes. Okay. And make it that will make it feasible under pressure instead of the 15 minutes earlier. Secondly, add visual signals. Red equal to allergen in use and green equals to allergen free. Thirdly, implement allergen body system during high volume event that will give you mutual verification. Fourthly, change staffing policy. When people call sick on the day of the event, make it mandatory that you need three trained staff for every event that is over 100 people. And this will ensure adequate resources are available. And fifthly, or the finally, adjust event scheduling, like increase the time of the schedule to allow 30-minute buffer between allergen and non-allergen preparation. So here, the cook also will have enough time. Okay. And the result here, that restaurant will follow this design, and the result, zero allergen incident over 2 years across 15 locations. You see? Let's redesign the produce packer also, the system redesign. Instead of the traditional way of just disciplining the operator, now in the system redesign, they did the following. First, install real-time chlorine monitoring with digital display, and that will give you immediate feedback. Secondly, replace unreliable dosing system with reliable equipment. Third, implement automatic line stop if chlorine drop below minimum. This is, you are creating now a strong feedback loop here. Fourth, remove production throughput from operator performance metrics to eliminate the conflicting goals here. And finally, add buffer time to stabilize chlorine demand. And here you are reducing the variation. So the produce packer did the same and did all these steps, the redesign steps, and the results, chlorine control within the specification 99.8 of time. Okay? And the microbial count consistently is meeting target at this point. So you see, total system redesign. Disciplining the worker was not the solution, as you can see. All right, shall we design the other companies? Let's proceed with the design. Now, let's design the bakery. The system redesign here, instead of just adjusting detector sensitivity, they will do the following for system redesign. First, change performance metrics. Now, supervisors will be evaluated on zero metal contamination, not production volume anymore, and this will align the goals. Okay. Secondly, implement automatic reject verification. So every reject must be inspected and documented, and this will create accountability. Thirdly, install upstream metal detection before final packing. Now here you are creating early detection, so you will have less product loss. And finally, redesign product flow to reduce false alarm impact, and this will minimize production disruption. As a result of this implementation, this redesign, the bakery followed the same, and the metal detector sensitivity maintained at validated point, and false alarm rate dropped to 60%, okay, due to upstream detection. And now they have zero metal contamination incidents. All right, let's redesign the beverage manufacturing, okay, as our final company to redesign here. The system redesign, instead of just raising temperature by 2 degrees Fahrenheit, like what they did there, they will do the following in the system redesign. First, install multiple temperature probes across heat exchanger widths, okay? And that will give you, that will measure the spatial variation there. Secondly, redesign heat exchanger flow patterns to eliminate cold spots. So here, you are fixing the design flow itself. Secondly, thirdly, validate temperature distribution, not just single point measurement. So here, you are verifying the uniformity. And finally, implement this redesign across all the production for production that have the same problem, remember? So here now you are transferring the knowledge to the system wide. So the beverage manufacturer did the same, and as a result, there has been a uniform pasteurization across the entire production system, production stream. The mold incident went to zero across all the lines. That is a system redesign, not just raising temperature by 2 degrees Fahrenheit in one line, and others are still having problems. Okay. Now, the difference here in outcomes. Okay. First, in a traditional system, as we saw, the time to recurrence is between 3 to 18 months. And the cost of recurrence is high here because the failure will repeat itself, a lot of recalls, lost productions, okay, because the problem is still there. And that means there is no learning. When it comes to learning, it's minimal because the same problem will keep repeating itself. And sometimes it results in crisis. But in systems thinking or systems approach, the problem is eliminated or is rare when you calculate the time to recurrence. And then the cost of recurrence here is very low because it's just one time redesign investment. Okay. And there is a lot of learning, as we saw there. You transfer the knowledge to other part of the system. So there is a lot of significant learning there. All right. Now, this question here: why systems thinking works? Why do you think, after we demonstrate all these points, why systems thinking work? Well, traditional thinking fixes the symptoms because it addresses what you can see, the failure point. But system thinking eliminates root causes. It addresses what you can see, the system conditions that make failure likely or inevitable. You see the difference here? This is why the system thinking works. Secondly, traditional thinking is faster in the short term for quick fix and moving on. But systems thinking is faster in long term because the problem doesn't happen again and there is a lot of learning that can be transferred to other part of the organization. System thinking also works because traditional thinking works when problems are truly just isolated problems, okay? But system thinking worked when problems are patterns, and that's the most of the time is the case in the food industry, food safety, okay? Now the question for you: when you look at your recurring problems in your organization currently or in the past, the issues that keep coming back despite corrective actions, are you fixing symptoms there or eliminating system conditions? Now take that question to reflect on, then we move to the next slide. Now let's start the other slide. Well, we covered all these points. Covered this point, and we have covered those points. Now let's start the second slide. What system thinking is and what systems thinking is not. Systems thinking is widely misunderstood, so let's be explicitly clear about what it means in food safety system or food safety practices. First, food safety systems is the following. It is a wide, it's a way of seeing relationships, not just individual components. It is understanding how actions create consequences over time. It is recognizing patterns that repeat across different situations. And it is seeing how structure drive behaviors. So systems thinking is not the following. System thinking is not drawing complicated diagrams, as we saw with all these examples. And system thinking is not creating complex models. System thinking is not academic theory that is disconnected from practices. And you have seen with those examples. Also, system thinking is not only for what a specialist can do. Anyone can do it as long as you are seeking to understand the system and asking the right questions. Now, in food safety practice, what system thinking means actually? Let's proceed. As we saw in traditional thinking, the pattern of questions is the following in traditional way. First, to start the investigation, why did this person make this mistake? If the investigation found out the person made the mistake, then the people will conclude we need better training. And then what the traditional thinking sees there is individual incident, right? So the response to temperature deviation is to retrain the operator. Well, let's see the system thinking. As we saw, system thinking is start with asking question for investigation. What conditions make this mistake likely? All right. Let's say the mistake of the temperature deviation. It will start like this. What conditions make this mistake likely? And then why doesn't our current system support people to do the right thing? So here, the systems thinking sees pattern that connect incidents. That's what you are looking for. And the response to temperature deviation here, why do temperature deviation keep happening despite training? What is our system? What in our system makes this deviation likely? All right. So now you can see the questions lead to different and more effective solutions. All right. That's the systems thinking. Now let's explore the interconnections, the hidden architecture of food safety. As we start our module earlier, we said systems fail because they are implemented exactly the way they are designed. But there are hidden architecture that we need to explore together now, and let's dive deeper. First, let's look at the core concept. Interconnections represent the causal pathways, information flow, feedback mechanisms, and dependencies that determine how systems elements influence each other. Okay, that's the interconnection there. So in food safety, these interconnections create what the research that was conducted by Nayak and Watterson in 2019, they describe it as multi-layer structure with multiple interactions across and within hierarchical level. This means that failure rarely happen in isolation, but propagate through connected pathways. Okay? Now, Why interconnections matter more than elements. Let's explore the theoretical foundations together. Traditional HACCP, as we all know it, focuses on identifying critical control points, CCPs, as discrete elements. Okay? But ISO 22000 2018 plus 8.5.4 explicitly requires organization to understand the interaction and interdependencies of processes. So here, ISO 22000 2018 recognizing that control effectiveness depend on interconnections, right? Now, the research by Nayak and Watterson there in 2019 in Trade in Food Science and Technology, they demonstrated that the food system exhibit characteristics of complex adaptive systems or CAS, where the following are found. First, emergent behaviors arise from interconnections, not individual components. Secondly, small failures in interconnections cascade through the system. And thirdly, the whole system behavior cannot be predicted by analyzing parts in isolation. All right, I will demonstrate this now. The real world case study that we touched base in previous module, which is Blue Whale Creamery's Listeria outbreak between 2010 and 2015. Let me give you a background here. Blue Whale Creameries experienced a multi-layer Listeria contamination that resulted in 10 illness, 3 deaths, and a complete production shutdown in 2015. Well, the FDA inspection reports revealed they had all the required elements, and they are listed as they had hazard plans with identified CCPs. They had environmental monitoring programs. They had documented cleaning procedures. And they had trained personnel. And also they had laboratory testing protocol. Well, the interconnections that fail, which is documented in FDA form 483 observations, are the following. First, the information flow breakdown. Positive environmental test results were not systematically communicated to production management. So tests showed Listeria presence, but the interconnection between detection and response action, was broken. Okay. Secondly, the temporal disconnection. Cleaning verifications happen, but the interconnection between cleaning completion and production restart lack time validation, which means production resumed before adequate drying time, and that allowing moisture to support the growth of the bacteria. Thirdly, the spatial interconnection failure. The facility had separate zones, but the interconnection between zone management and traffic patterns was not controlled. That means personnel and equipment moved between zones without adequate barriers, and they carried the contamination. Finally, there was feedback loop failure. When finished product tested positive, the interconnection between positive result and environmental investigation was weak. They addressed the immediate batch but didn't trace back to environmental sources. The critical insight here from this background, the system behaviors emerge from interconnections. All right. Now let's look at that together. Bluebell had invested in sophisticated testing equipment, which are element, but failed to establish the interconnection between data and corrective actions authority. They had cleaning chemicals, another element, but the interconnection between chemical concentration and application technique was not verified. And then they had zone separation, another element, but the interconnection between zone through air handling systems was not controlled. You see that? Now, let's see the interconnections in ISO 22000 2018 framework for effective application. The standard addressed this by emphasizing on the following: address the interconnection. First, in clause 4.4, understanding the organization's context requires mapping interconnections with external parties, right? Secondly, clause 8.2, prerequisite program must address interconnections between programs. And thirdly, in clause 8.5.1.5, the hazard analysis must consider the likelihood of occurrence of hazard in relation to the severity of their adverse health effects. And this is an interconnection between probability and consequence. Now, the mapping the interconnections. When we want to map the interconnections, we have to ask practical questions. Let's go through the questions that we should ask to map the interconnections. Uh, First, we need to ask this technical question: the temporal interconnections. Time gap creates risk. And the question we should ask here: what is the maximum time delay between control action and verification? What happened product safety during this interval? Let's demonstrate that with example. Small farm. Okay, in a small farm. Dairy farm cools raw milk immediately after milking. That's a control action. But they only check temperature log once per day during morning milking time. That's their verification. Well, the time gap there between the control and the verification is up to 24 hours, right? Now, what happens during this interval? If the cooler malfunctions at 2 a.m., for example, 2 p.m., the milk will sit at unsafe temperature for 18 hours before anyone notices. By then, bacteria count would have multiplied around 10,000 fold or 1,000 fold. So the temporal interconnection here, the time between cooling and verification, created a window where problems amplify undetected. See that? Now another example with lat manufacturer. A ready-to-eat meat plant products environmental monitoring swapped on Monday. That's their control action there to detect the contamination. But the lab results return on Thursday. That's the verification to confirm the environment is clean. What happened there? The time gap there is 3 days, right? Now, what happened during this interval? If Monday's swab detected listeria, for example, That means production continued Tuesday, Wednesday, and Thursday using potentially contaminated equipment. 3 days of products are at risk before anyone knows there is a problem. So the temporal interconnections here, a swap to result, is too long for effective control, right? Now, second technical question will be asked is considering information interconnection. Who knows what and when? The question here you should ask to map this interconnection is who received critical data, in what form, within what time frame, and what was decision authority do they have? Let's explore. In restaurant chain example, a catering kitchen has a critical allergen order. The order is non-nuts, severe allergy. The information flow here, first, customer tells the sales rep, verbal, and then the sales representative emails kitchen manager. The email went the same day, and then the kitchen manager posts note on order board by physical paper the next morning. And then the line cook reads note before the preparation. That's through visual, the day of the event in the kitchen. Now, the breakdown of interconnection here, line cook has information but not the authority to stop the production of not contaminated equipment if not contaminated equipment was just being used. So, and what they need to do there, first they must ask the supervisor, and who must ask the manager, who must call the customer, and by then the food is already prepared. Here, what decision authority do they have here? None. Information reach the person doing the work, but authority uh, to authority to act remain three levels up. The interconnection between knowing and acting is broken in this case, right? Now, let's demonstrate with another example. Beverage manufacturer. The juice plant has automated pH monitoring, which is critical for pathogen control. The information flow here, pH sensor will read 3.8 and the target is 3.5 or below. Then the data log to computer system, real time, immediately. Then quality manager logs end of the shift, that's after 8 hours. The quality manager will review the log after the end of the shift, after 8 hours. Then the quality manager, after reviewing the logs, notifies the production supervisors the next day. Then the production supervisor investigates 2 days after the deviation. Now, the broken interconnection here, critical data exists in real time, but reach decision makers after 8 hours. And the person who could act immediately, the line operator, doesn't receive the information. So the person who received the information, who is the quality manager, isn't present to act immediately. What decision authority do they have here? Quality manager can stop the production, of course, but only after 8 hours delay. An operator could act immediately but has no access to the data. You see? Thirdly, to map, if you want to map the physical interconnections of how hazard moves, you will start with this question. What pathways for hazards to move from one location to another? What controls exist at each interconnection point? Let's demonstrate that with example. Small processor, a small cheese plant has separate rooms for raw milk receiving and finished cheese packing. The physical interconnection pathways here. The first pathway, personnel walk from raw areas through hallway to finished area. The control at interconnections, hand wash, sink in hallway. The gap here, no requirement to change shoes or outer garments. In second pathway, cleaning equipment, mops and buckets are used in raw area, then stored in shared closet, then used in finished area. The control at interconnection here is none because the same equipment are used in both areas. The third pathway, air handling systems draw air from raw area through shared ductwork into finished product. The control at interconnections here is none. No air filtration or pressure differential. The result here, three physical interconnections carry contamination from raw to finished area despite having separation rooms. So the spatial separation, which is element, exists, but the interconnections, which are pathway, undermine it. Another example from a large facility. A multi-line food plant produces both containing and allergen-free products. The physical interconnection pathways include the first pathway, ingredient delivery from ingredient delivery truck to receiving duct and to ingredient storage. The control here, allergen ingredient are delivered on different day. But the gap here, the same duct, same forklift, and same storage area. Sequential use here creates cross-contact risk. The second pathway, production line A contains nut and have shared ingredient scale with production line B, which is peanut-free. The control here is to clean the scale between uses. But the gap, the scale has crevices that retain peanut particles despite cleaning. The third pathway is finished products from line A have shared conveyor to packing, and uh, and line B also product have the same shared conveyor. The control here is to learn allergy free products first, then allergen products. But the gap here, that doesn't prevent carryover if schedule change or line runs late. The results? Five physical interconnections create allergen cross-contact risk. So each interconnection point needs a specific control, but only some have them. Fourthly, to map dependency interconnection that cascade the failure, we need to ask the following question. If one control fails, which downstream controls become inefficient? What is the cascade pathway here? Let's start with the example of poultry processor. A chicken plant has multiple controls in sequence as following. The control chain, first, receiving inspection, reject bird with visible fecal contamination. Secondly, evisceration, which remove intestine without rupture. Third, chill tank to reduce temperature and wash the carcasses. Fourthly, antimicrobial spray to reduce surface bacteria. And finally, the final inspection through visual check. Now, the dependency cascade if control 1 fail in this case here. Let's demonstrate. First, receiving accepts heavy contaminated birds. Let's assume the first control fails in this case, right? Then what happened? Evacuation spreads contamination to equipment and other carcasses. Thus, control 2 will be overwhelmed. Thirdly, chill tank water becomes heavily contaminated. Thus, control 3 overwhelmed. Then, antimicrobial spray can reduce high bacterial load to safe level. Thus, control 4 overwhelmed also. Then, the final inspection can see microbial contamination. Thus, control 5 will become ineffective. Now, the dependency interconnections here, each downstream control depends on upstream controls to limit the contamination to manageable level. But when control 1 fail, the entire chain become ineffective because each control has maximum capacity. And if you exceed that, the control will fail. Let's demonstrate the same point with a bakery. A bakery has metal detection as the final control before packing. Okay. The dependency chains here as following. First, upstream control 1, ingredient suppliers screen ingredients for metal. The second upstream control 2, maintenance removes worn metal parts before they break. Upstream control 3, metal detector cuts any metal that enters. Downstream control here, product packing and distribution. Dependency cascade here if upstream control 1 and 2 fail. Let's demonstrate. Supplier doesn't screen ingredients. That means the metal will enter the facility. If maintenance doesn't replace worn mixture blades, then the blade fragments break off. And if metal detector must catch both source of metals, ingredients, and equipment, the metal detector sensitivity will be set to avoid false alarm from ingredient metals with high frequency. Now, equipment metal fragments are smaller than the detection threshold itself, so the metal reaches the consumers. Here, the dependency interconnections, the metal detector's effectiveness depends on upstream controls limiting metal sources. When upstream control fails, the final control is overwhelmed or must be set less sensitively to avoid false alarm. So this will reduce its effectiveness. Okay. Let's demonstrate the point number 5 when you want to map the interconnections of feedback of which information returned to drive decisions. Okay. To map the feedback interconnections, you ask the following question. You start with this. When a deviation occurs, what information is returned to the decision maker And what is the response time required? Now let's demonstrate that with cold storage example. A cold storage warehouse maintains product at 35 degrees Fahrenheit. The feedback interconnections here are as following. First, deviation occurs. So temperature rises to 40 degrees Fahrenheit. So as a result of compressor malfunctioning. Then information returns. Temperature sensor sends data to monitoring system. Then decision maker receives alarm sound in control room. Then response time requirements must respond within 30 minutes so that before the production temperature rises above the safe threshold. Okay, that's the feedback interconnections here. Now, the strong feedback interconnections in this case will look something like this. From sensor to alarm to operator to actions should take 5 minutes. And also, the operator has the authority to call maintenance immediately, and maintenance respond within 30 minutes, and product temperature control before safety compromises, right? But the weak feedback interconnections will look something like this. From sensor to daily log review to manager notice next day, that's 24 hours. Then manager must get approval to all the maintenance. Then maintenance will be scheduled when available, let's say for after 3 days. Then the product temperature abuse for 3 days before the correction happen. Now, the feedback interconnection here, the speed and authority of the feedback loops determines whether deviations are corrected before causing harm. Strong interconnections happen in minutes, but the weak interconnections evidently happen in days. Another example for from produce packer. A lettuce packing facility monitors chlorine level in washed water. The target here is between 100 to 150 ppm part per million. The feedback interconnections happen as the following. Deviation occur, chlorine drops to 75 ppm, that's below the minimum. The information returned, how and when does operator learn about this? In the weight feedback, this is what happened, which is common. First, operator takes manual sample every 2 hours, then sample sent to lab, then lab results returned 4 hours later. Then by then, 6 hours of lettuce washed in inadequate chlorine. That's the common way, right? Now the strong feedback will look something like this, the improved feedback. First, inline sensor measures chlorine continuously. Then digital display shows real-time level. Then alarm sounds when below 100 ppm. Then operator sees deviation immediately in seconds. Then operator authority has authority to stop line and adjust the chlorine. And verification happen display will show the return to 100 ppm or over 100 ppm in minutes. Now the feedback interconnection here, strong feedback means information returns to the decision maker in seconds with authority to act. The weak feedback means hours of delay and no clear authority. The interconnection's speed determines how much product is affected in this case, right? If you notice the pattern there, in every example, The interconnection determines system behavior more than the individual elements, right? First, in temporal interconnection, the time between the time gap between action and verification determines risk exposure. That in information interconnections, who receives data and their authority determines response effectiveness. That in physical interconnections, the pathway between areas determines contamination is spread. Then in dependency, upstream controls effectiveness determines downstream control capacity. And in feedback interconnections, information is speed and decision authority determine corrections is speed. This is why system thinking focus on interconnections. The elements might all be present. You could have controls, procedures, and equipment, but if the interconnections are weak or broken or delayed, the systems fail, right? You are tasked now, map the interconnections in your system, okay, in your organization, and don't just list your control. Trace how they connect, how information flow, how hazard moves, how controls depend on each other, and how feedback return to drive decisions. Here, let's connect to Module 3, patterns, the 5 failure patterns. We are here, the interconnections, like each interconnection is connected to patterns. For pattern 2, which we studied in Module 3, the interface failure, interface are interconnections. For the demonstration of the Peanut Corporation of America, the outbreak of 2008 to 2009 showed interconnection failure between certificate of analysis and actual product safety. The interconnections between documentation and reality broke. Then pattern 3, which is probably moving forward. This is interconnection behavior. Contamination at receiving propagates through processing because interconnections, material flow, and equipment contacts and personnel movement carry the hazard forward. Thirdly, pattern 4, symbolic evidence. The interconnections between evidence collection and evidence interpretations breaks. Organizations collect data, which are element, but interconnections to decision making is symbolic rather than functional. Pattern 5, which is pressure wins, product production pressure dispute interconnections by producing time constraints that break verification loops, skip cleaning step, or override whole pressure procedures. Now, the design implication here, engineering robust interconnections. Effective food safety design requires engineering interconnections with the same rigor as designing control points. And this means the following. First, defining information flow protocols with specified time and authority. Secondly, establishing physical barriers that control material and personnel interconnections. Thirdly, creating feedback loops with defined response criteria and timeframes. Fourthly, validating that interconnections function under production pressure conditions. And finally, monitoring interconnections integrity, not just elements presence. And this according to the reference that we went through. from Nyack and Watterson, 2009, in global food safety as a complex adaptive system, key concepts and future prospects, which was established in trends in food science and technology. The problem with linear thinking. Let's explore the problem with the linear thinking. Okay. Now, let's explore together the problem with linearity, the limitation of linear causality in food safety. First, what is the seductive appeal of linear model or models? Linear cause and effect thinking dominates food safety training nowadays, or usually, or always, because it offers psychological comfort. Actually, it goes like this: if we can identify the cause, we can implement the solution. But this reductionist approach inherited from 19th century industrial engineering. And this approach assumes that complex systems can be understood by breaking them into component parts and analyzing each in isolation. Now, the structure of linear thinking in food safety, conventional HACCP training presents food safety as a linear sequence. It goes like this: from raw materials to processing to packing to distribution to consumption. That's the conventional HACCP training presents the food safety as a linear sequence like this. And at each step, hazards are identified and controls applied. The implicit assumption here controls the hazard at each point and the system is safe. Just apply a control and you are safe. That's the implication here. This is a linear causality because they say like cause A cause like point A or hazard A causes hazard B and B causes C and therefore controlling A means controlling C. Well, why this failed? Let's examine here the Jack DeCoster egg outbreak of 2010. Let's break it down and study that what happened there. A little bit of background for the Jack DeCoster egg outbreak in 2010, and you can find this and read it online. The right country egg and Hillandale Farms, which is owned by Jack DeCoster, caused the largest salmonella outbreak in the USA history. Approximately 2,000 illness from contaminated eggs. Linear thinking would suggest here that salmonella in egg, that means implement egg washing and refrigeration, and the problem is solved. That's the linear thinking. But the FDA inspection revealed a non-linear system failure, which we are going to examine today and demonstrate it and show also the implementation. First, let's say from the FDA inspection report, the actual system behavior here, the feedback loop. There was a rodent infestation, and from rodent feces contaminated feed, and feed contaminated hens, and hens laid contaminated eggs, and egg sold, and no feedback to address rodent problems. And then the rodent populations increase and the contamination worsen. That's the feedback loop. Now, this is a reinforcing loop, not a linear chain. Each cycle made the problem worse, evidently, right? Second behavior, the multi interaction pathways. The pathway A from rodent feeds, and from feeds to hens, and from hens to egg. That's pathway A. Pathway 2 from rodents to environmental contamination, eggs contact surface to egg. The third pathway, or the pathway C, is from flies to manure to environmental spread to egg. The pathway D is from inadequate cleaning to biofilm formation to persistent contamination to eggs. Now, these pathways interacted. Controlling one pathway didn't stop contamination because the other pathway compensated. This is non-linear system behavior, right? First, we have delay effect. Contamination introduced in pullet nearby facility or chicks nearby facilities didn't manifest as human illness until months later after eggs reached consumers. The delay between cause and effect broke the linear mental model here because the operator couldn't see the connection between their actions and outcomes. So, the theoretical problem here, complex adaptive systems don't obey linear rules. So, food system exhibit characteristics of complex adaptive systems or CAS. And those characteristics are as following. First, nonlinearity. A small input can produce large output, which means one contaminated ingredient affects thousands of finished products. Secondly, the feedback loop characteristic. System outputs influence input. So contaminated environments recontaminate cleaned equipment. Thirdly, the emergence. System level behaviors arise that cannot be predicted from component analysis. Means persistent Listeria harbored emerged from interactions of moisture and nutrition and cleaning practices, right? The fourth characteristic is adaptation. System elements respond to interventions in unexpected ways. So, which means, for example, bacteria develop biofilms in response to cleaning pressure, right? Now, why do you think uh, linear HACCP often fail? Well, let's explore together. The traditional HACCP, as originally conceived from NASA in the 1960s, was designed for relatively simple linear process, which was thermal processing of self-stable foods, right? But when applied to complex models of modern food systems, it encounters fundamental limitations. And those limitations are as following. First, CCP identification assumes independence. CCP identification assumes independence because CCP decision trees evaluate each hazard control pairs independently, but in real system, controls are interdependent. For example, metal detection, which is CCP, for example, effectiveness depends on product temperature and moisture content and conveyor speed also, all influenced by upstream processes. Second limitation, critical limits assume static conditions. Now, CCPs have defined critical limits, for example, cook to 165 degrees Fahrenheit. But system dynamics mean conditions vary. And we have this study by Gonzala, Rodriguez Gonzala in 2014, which came out recently. In food production trends showed that 73% of HACCP deviations occurred not because critical limits were wrong, but because interconnections factors such as equipment variability, ingredient variability, and operator decisions created conditions where the limits couldn't be achieved. The third limitation is verification assumes that cause affects clarity. ASAP verification checks if control works, but in nonlinear systems with delays, verification at time T, for example, doesn't reveal problems that will manifest at time T plus 30 days. You see, for example, the environmental contamination, right? Now, let's examine the cantaloupe listeria outbreak of Jensen Farms in 2011. The linear thinking meets system complexity here. In case of Jensen's Farms cantaloupe outbreak, which causes 33 deaths, the deadliest foodborne outbreak in U.S. modern history, what happened there? The linear thinking applied. Cantaloupes have rough surfaces, right? So the wash cantaloupes, the, again, the cantaloupes have rough surfaces. And the linear thinking applied here, wash the cantaloupes and the problem is solved. Well, the non-linear reality from FDA investigations revealed the following. First, the purchased used potato washing equipment. That equipment is designed for soil removal, not for pathogen reduction. First thing. Secondly, the equipment had dead-end pipes that couldn't drain. You can see there, the chlorine wasn't used also, and the reason they wanted to reduce the cost. That's a cost decision. And then also the cantaloupes were stored in a facility with truck traffics, which were introducing soil, from coming from outside and introducing the contamination, the dust with the dust. Okay. Now, the cooling system created condensation that dripped into clean cantaloupe in the store. So the system behavior here, each element alone was manageable, but the interaction created the catastrophe. Let's demonstrate. The rough cantaloupe surface plus inadequate equipment produces incomplete cleaning. Then the incomplete cleaning plus no antimicrobial produces bacteria survival. Then the bacterial survival plus moisture from condensations produces bacterial growth. Then bacterial growth plus storage time plus temperature produces high contamination levels. Then high contamination plus vulnerable population produces death. Now, this is multiplication. It's not additive because linear thinking adds risk. For example, risk A plus risk B plus risk C. But the system thinking recognizes multiplication. Risk A multiplied by risk B multiplied by risk C. That's the case here. Let me go back a little bit here. Sorry, I have issues with some the slide here. Okay, let's come here. We covered this point. Where were we? Yep. Now, the mathematical reality here in linear system, the output k equals to k multiplied by input. Okay, the factor here multiplied by input, and that would produce proportional relationship. But in nonlinear systems, output equals to f, which is the the process of the interaction that combine inputs and feedback and time and interaction, where f, the process, is often exponential or chaotic, right? Now, food safety systems are nonlinear because of the following. First, bacterial growth is exponential, not linear. Secondly, contamination spread follows network patterns, not linear path also. Thirdly, human decision making involves thresholds and tipping points. That's also it's not a proportionate response. Fourthly, system failure often results from coincidence of multiple factors, including multiplication and not additives, right? Now, the implication for food safety practice. Linear thinking is not wrong. First of all, let's clarify that, but it's incomplete. It worked for simple, stable, isolated processes. But modern food systems, as we all know, are not simple, stable, and isolated processes. Modern food systems are, first, globally interconnected. Ingredients come from multiple countries, right? Modern food systems also are dynamically changing. The production schedules, the personnel change, the equipment conditions. Okay. And thirdly, the modern food systems are subject to multiple simultaneous pressures, including cost, the pressure of speed, the pressure of quality, the pressure of safety, right? Now, these characteristics demand systems thinking. We must move from asking what caused this failure to what system conditions allow this failure to emerge and persist. You remember from the beginning of this module, right? That's where we need to move to. This shift again from linear causality to system dynamics is the foundation of effective food safety management in complex modern food systems. And we are referring to those studies that we mentioned earlier. Now, let's move to foundational concepts. Food safety as a complex adaptive system. Now, let's see the theoretical foundation and practical implications here. Defining complex adaptive system in food safety context. How does it happen? It's like this. Complex adaptive system or CAS is a system composed of multiple interacting agents that adapt their behavior based on experience, where system levels patterns emerge from these interactions in ways that cannot be predicted by analyzing individual components. So food safety systems meet every criterion of a CAS here, or complex adaptive systems. Yet most food safety management approaches treat them as simple, linear, controllable systems. And that's a fundamental mismatch that explains Persist's failure, and we will solve it together. Let's go back again to the theoretical framework of Nayak and Watterson in 2019 in their seminal of 2019 paper in Trend in Food Science, which we touched base earlier, Food Science and Technology. Nayak and Watterson systematically demonstrated that global food systems exhibit all defined characteristics of complex adaptive systems. First, the multiple interaction agent. Okay, these characteristics of CAS food, food system involve farmers, processors, distributors, retailers, regulators, consumers, and microbial populations. And each agent makes decisions based on local information, and these decisions interact to produce system level outcome. Let's consider this example. A processor decides to extend shelf life. That's a business decision, which lead to formulation change, okay, causing the pH to increase slightly. This increases Listeria's growth potential, right? Especially as retail storage temperature varies and consumer storage also practices are different. Ultimately, illness risks emerge from complex interaction of all these agent decisions rather than from any single fault. See here? The second characteristic here is nonlinear dynamics. Small changes can produce disproportionate effects. For example, a mere 2 degrees Celsius temperature increase during distribution doesn't increase bacterial growth by 2%. We all agree that it can increase it by 200% or more due to exponential growth kinetics. And this means that effects aren't always proportional to their causes, right? The third characteristic here is emergence. System levels behaviors often arise that no single agent intend or predicted. Powerful example for that is the phenomenon of persistent Listeria herbicides, which emerged from the intricate interaction of facility design, cleaning practices, production schedules, and bacteria adaptation. No single factor creates this persistence. Rather, it is their dynamic interactions that allows it to develop and persist. The fourth characteristics of our modern food safety that exhibit, which match with CAS, is adaptation. System elements learn and change over time. Bacterial populations adapt to cleaning chemicals by forming biofilms and developing sanitizer resistance, right? Similarly, workers adapt to production pressure, sometimes leading to shortcut behaviors, and management adapts to audit findings, often with documentation improvement that may not reflect actual practice changes, right? Wonderful. Now, the fifth characteristic of our modern food safety that exhibits is self-organization. Patterns form without central control. For example, information communication networks often develop among workers, where they share information about how things really work. These networks can either support or subtly undermine formal food safety systems. And this demonstrating how complex behaviors that arise ori- uh, uh, organically within the system. Now, the question is why this matter? The limitation of traditional approaches? Well, traditional food safety management, rooted in HACCP, which is developed in 60s, assume the following. Assume that systems are controllable through defined control point, that cause-effect relationships are clear and stable, that verification at one point in time ensures ongoing controls, and that documentations reflect reality. Well, these assumptions work for simple systems, for example, a single thermal processor in controlled environment. They fail for complex adaptive systems because of the following. Assumption one fails. You cannot control a control adaptive system. You can only influence it. Control points are nodes in a network, and networks behavior emerge from interactions, not from individual node performance, right? Assumption two fail. In CAS, cause-effect relationships are context dependent and change over time. What worked yesterday may not work today because the system has adapted. Thirdly, assumption three fail. Verification capture a snapshot, but CAS are dynamic. The system state at verification time may not represent the system state during production. Also, assumption 4 fails because in CAS, there is often a gap between work as imagined, the documented procedure, and work as done, actual practice in reality, because workers adapt to local conditions. Now, the real world evidence, let's explore the Listeria persistence problem from the real world, right? So in 2021, Cornell University study, uh, which was conducted by Bella and Wademan and Sullivan for food protection trends, investigated Listeria persistence in an house using root cause analysis. They found the following. First, they found the complex system behavior as 16 different Listeria allelic types were isolated, high diversity. Yet, the same locations repeatedly test positive. Traditional thinking would say persistent strain kill the strain, right? Well, system thinking would say persistent system conditions will change the condition. Don't kill the strain, change the condition, like we did earlier, right? The root causes here, system level one, system level, the root cause. The facility, this is what they found. The facility had cleaning procedure element, but the system condition that allowed persistence were first, forklift stop created microenvironment where moisture accumulated. Secondly, floor cracks provided protected niches. Thirdly, cleaning frequency, which was conducted once weekly, allowed biofilm establishment between cleanings. And fourthly, the interaction of these factors created conditions where Listeria could persist despite cleaning. The system intervention here, instead of just cleaning better, elements focus in the traditional way, they did the following. First, increase cleaning frequency to twice weekly. This change in temporal dynamics. Secondly, applied quarterly ammonium powder before cliff stop to change microenvironment. Okay. Thirdly, they removed dead end pipes, so they eliminated the niches there. And fourthly, the interventions change system conditions here. These interventions change system conditions and not just individual elements. Now, the results here, the Listeria was eliminated from previously persistent sites, and now it becomes 0 out of 5 sample positive after intervention. But before the intervention, they have 6 out of 10 positive. Now, let's take a look of how ISO 22000-2018 recognition of system complexity. The 2018 version of our ISO 22000 represents a shift towards system thinking through, though it doesn't explicitly explain or use the CAS terminology, it does the following. First, in clause 4.1, understanding the organization and its context requires understanding external and external issues relevant to its purpose and strategic direction, right? That's understanding the organizations and its context. This is the ISO requirement in class 4.1. This recognizing that the food safety system is embedded in larger system that is business, regulatory, and social, and must adapt to changing contexts. Also in clause 4.2, which is understanding the needs and expectation of interested parties, ISO recognizes here multiple agents, interested parties, with different goals that interact to influence system behavior. And also in class 8.5.1.5, the hazard assessment, which requires considering the likelihood of occurrence of hazard and the severity of their adverse health effects. This is acknowledging that hazard realization depends on system conditions, the likelihood, not just the hazard presence, right? Also, in clause 9.1, monitoring, measurement, analysis, and evaluation requires analysis and evaluation of appropriate data and information arising from monitoring and measurement. This is recognizing that understanding system performance requires analyzing patterns and trends, not just checking compliance at individual points. The practical implications here for food safety professionals: understanding food safety as CAS, complex adaptive systems change how we approach management, as the following. First, from control point to influence network. So don't ask, what are my CCPs? Instead, ask, what are the key interactions in my systems and how can I influence them? And then also, you can move from static procedures to adaptive protocols. So don't create rigid procedures that must be followed exactly. Create protocols that define principles and allow adaptation to local conditions while maintaining safety. We will demonstrate all these points as we progress, okay? But now this is how we should approach the management, okay, as a cast the change. Thirdly, we approach from compliance verifications to system monitoring now. We move from compliance verification to system monitoring. So don't just check, did we follow the procedure? Instead, monitor the following. Is the system producing safe food? What patterns indicate system health or degradation? Then move from root cause, singular, to contribution factors, multiple. Don't ask what caused this failure. Ask the following. What system conditions allowed this failure to change? What interactions created vulnerability? And then from blame to system redesign. So don't conclude, for example, worker error caused the problem. Conclude the following. System conditions made error likely. How do we redesign the system to be more resilient? Okay, now let's explore the research frontier here. Again, in Nayag and Watterson, propose using system theoretic accidents model and processes STAM for food safety analysis, a method designed for complex systems that focus on the following. First, focus on control structure, how decisions flow through the system, and also focus on feedback loop, how informations return to influence decisions, and also follow on constraints, what limits systems behave, and then also focus on adaptation, how the system change over time. These represent the future of food safety science, moving from reductionist analysis of individual hazards and control to holistic understanding of the system dynamics, right? The implication here, food safety professionals must develop system thinking capabilities, the ability to see patterns, understanding feedback, recognizing emergencies, and designing interventions that work with system dynamics rather than against them. And we are referring back to the same studies again. Now, this is our signature section here, hazard flow dynamics. We are going to move from a static list to dynamic system behavior. The fundamental paradigm shift here. Traditional food safety treat hazard as static entities to be identified and controlled at discrete points. Systems thinking recognize hazard as dynamic flow through interconnected pathways, where hazards behavior emerge from system conditions rather than existing as fixed properties. This shift from hazard list to hazard flow dynamics fundamentally changes how we design food safety systems. Now, let's first take a look at traditional approach, the hazard list paradigm. HACCP step six steps, uh, according to the version that developed by Codex Alimentarius in 1997, an FDA food code requires conducting the step number six. Sorry, let me go back. Hazard step six that's developed by Codex Alimentarius in 1997, an FDA food code requires conducting hazard analysis, which typically produce the following. First, biological hazards that include salmonella, listeria, monocytogenes, E. coli, uh, Cambrylep, sorry, Campylobacter, sorry, I'm bad with this one here, and nervous and parasites. And then also, it requires chemical hazards, analysis of chemical hazards, including allergen, mycotoxin, pesticide residues, cleaning chemical residues, and heavy metals. And then also the analysis of physical hazards, which include glasses, metal, plastic, bones, and wood. This list-based approach assumes the following. Hazard can be identified independently of system contexts. Each hazard has fixed characteristics, severity, and likelihood. Control can be applied to individual hazards in isolation. Controls hazard at identified point measures safety. And these assumptions breaks down in complex food system. So now let's, because this hazard breaks at the breakdown in complex food system, let's explore the dynamics perspective here in hazard flow dynamics. Hazards don't exist in isolation entities. The flow through food systems along pathways determined by, first, the material flow, ingredient, packing, water, and air. Thirdly, determined by energy flow, heat, cooling, mechanical energy, and by information flow, including specifications, test results, decisions, and by personal flow, movement, patterns, shift change, training, etc., and by time dynamics, including production schedules, historic durations, and seasonal variations. Now, hazard behaviors emerge from the interaction of hazard characteristics with system conditions. Okay? In the real world case study, the 2008 and 2009 Peanut Corporation of America salmonella outbreak, this outbreak caused 9 deaths, 714 illness across 46 states, and almost 4,000 product recalls. the largest food recalls in US history at that time. Now, the traditional hazard analysis would identify the following. First, micro uh, biological hazards include like salmonella in raw peanuts, and then control roasting to achieve 5 log reduction, and then verification, finished products testing. That's the traditional hazard analysis would identify like that. Now, the actual hazard flow dynamics from congressional investigation and FDA inspection, the those are the flow pathway. The first flow pathway was environmental contamination to product. The roof leaked, introduced water, and then water contacted the surface, and then the surfaces harbored salmonella, and then the product contacted the surface during the processing, and then contamination transferred to product after roasting. Okay? The flow pathway number 2 was from positive test to retest to release. What happened? Product tested positive for salmonella. Then, instead of investigating source, the product was retested again. And then the retesting continued until negative result obtained. And then the product was released based on the negative results. Then the contaminated product entered the commerce. Okay. The flow pathway number 3 is information suppression. The positive test result existed, right? But information didn't flow to decision makers who would hold the production. And the information flow was also deliberately blocked. So hazard information couldn't trigger protective responses. The system behavior here, salmonella didn't just exist in the facility. It flowed through multiple pathways. First, the physical flow from environmental to equipment to product, and the temporal flow from contamination persisted over years from 2007 to 2009. And the information flow, the test data to suppression to continued production, and the decision flow from positive results to retesting decisions to release decision. Now, each pathway had velocity here, how fast hazard moves, and also has volume, how much contamination, and also has persistence, how long it lasts. Traditional hazard analysis doesn't capture these dynamics. The hazard flow characteristics technical framework. To understand hazard flow, we have to analyze these dimensions. First, flow velocity. How quickly does hazard move through the system? As the question, Salmonella liquid egg is rapid, hours from contamination to distribution. Secondly, Listeria environmental contamination is slow, months to establish and years to persist. And allergen cross contact, instantaneous, right? Single contact event. Now, the implication here, control timing must match flow velocity. Slow moving hazard requires continuous monitoring, and fast moving hazard requires real time control. Secondly, the flow volume. What is the magnitude of hazard transfer? The low level contamination from 1 to 10 colony forming unit or CFU per gram versus high level, which is over 1,000 CFU per gram. Okay, and the effects there: illness severity, detection probability, and control effectiveness. The implication here: controls must be designed for worst case flow volume not average condition. Third, the flow pathway. What routes does this hazard flows? Direct pathway from ingredients to products, that's linear. Indirect pathway from ingredient to environment to equipment to product, that's network. And feedback pathway from product to environment to next production run, that's cyclical. The implication here, we must map all pathways, not just obvious direct route. The 2011 Jensen Farms Cantaloupe outbreak showed indirect pathway, right? As we demonstrated earlier. Condensation drip was the critical contamination route. Fourth, the flow amplification. Does hazard concentration increase or decrease? The amplification here, bacterial growth during temperature abuse. Dilution, mixing contaminated ingredients into large batch. Concentration, evaporation, and reduction processes. The implication here, the time temperature dynamics determine whether low-level contaminations become high-risk exposure. Fifth is flow persistence. How long does hazard remains in system? Transient contamination clears with cleaning cycle. Persistent contamination survives cleaning, recontaminate product. And then resistant contaminate contamination becomes established in facility environment. The implication here, persistent hazard requires system redesign, not just enhanced cleaning. As you can see, persistent zone area where water pressure build and force flow, leak point valves join and seal, prone to bacteria and contamination pathway routes, enabling spread through processing line and accumulation is area sum and low flow packet where sediments collections or collects. Here, let's look at application of hazard analysis. ISO 22000, uh, ISO 22000 and 2018 class 8.5.2.3 requires hazard assessment to consider the following: severity of adverse health effect and likelihood of current of occurrence. The flow dynamic determine both. Severity is influenced by flow volume, contamination level, flow amplifications, growth during distribution, flow pathways, which products or consumers are affected, and also the likelihood is influenced by flow velocity, how often contamination occurs, flow persistence, how long contamination lasts, and flow pathway complexity, how many routes exist. Traditional hazard analysis treats these as static properties. Flow dynamics recognizes they are system-dependent variables. The practical tool here, hazard for hazard flow mapping. Instead of creating hazard lists, create hazard flow map. So step one, identify hazard sources, not just salmonella, but where does salmonella enters the system, for example. Let's assume from raw material, which one? What prevalence. Through environment, which area, which conditions support it? And if it enters the system through personal, what behavior introduced it? Then the second step is to map the flow pathways. Trace how hazard moves, material contact sequences, map also the equipment sharing patterns, the personnel traffic routes, and airflow patterns, and water condensation movement. And then step 3, identify flow characteristics. For each pathway, identify velocity, how fast. For volume, identify how much. Uh, for amplification, does it grow? Identify also persistent, how long? And then step 4, identify flow control points. Where can you block the flow? Bacteria uh, through barriers or through separations? How can you reduce the flow? Through cleaning, sanitations? How can you eliminate hazards? Thermal processing, chemical treatment? And how can you monitor the flow? Testing and verification. And then step 5, design flow responsive control. Controls must match the flow dynamics, must be fast. Fast flow needs real-time controls. High volume flow needs robust controls. Persistent flows need system redesign. Multiple pathways need network controls. Case example, Listeria flow in ready-to-eat processing. In ready-to-eat meat processing, Listeria flow analysis revealed the following. The primary flow is from material to cooking, kill step, to cooling, to slicing, to packing. Okay? Now, the traditional thinking here would be cooking, kill Listeria. So, post-cooking, which is cooling, slicing, and packing, uh, is safe, or they are safe. Well, the actual flow dynamics are the following. Flow pathway A from environment to slicer to product. That's a post-cooking contamination right there. The flow pathway B from slicer to product to slicer. That's a cross-contamination between batches, right? Then the pathway C from condensation to sealing to product. That's drip contamination. And then from personal hands to products. That's handling contamination. Now, the flow characteristics here, the velocity is slow. Environmental listeria establishes over weeks. The volume here is low initially, but amplifies if product temperature abuse. Resistance is high here, caused by biofilms in a slicer and flow drain. And pathway here are multiple, interconnected. The flow responsive controls here first block environmental flow, physical barriers by physical barrier and zone separation, then reduce slicer flow, enhance cleaning frequency, and also conduct ATP monitoring. And then eliminate condensation flow by conducting facility design and air handling. And then monitor flow, environmental monitoring program targeting flow pathways. This is fundamentally different from control listeria at CCP. It is managing hazard flow through the system. Now, did you see the difference here? Great. Let's move The next conclusion, the paradigm shift here, moving from hazard lists to hazard flow dynamics requires the following: thinking in pathways, not points. Okay, as we demonstrated, understanding dynamics, not just presence or absence, and also designing system level controls, not just elements level intervention, and also monitoring flow patterns, not just testing uh, endpoints. So this shift align with how hazard actually behave in complex food systems as a dynamic flow through interconnected pathway, not static entities waiting to be controlled. Right now, let's move to critical understanding. Boundaries create blindness. This is what we need to explore deeply right now. Now, let me just adjust here. The critical uh, the boundaries creation is critical, and we need to study this thoroughly. Do you know why we create boundaries? And by boundaries, we have in our modern food system, boundaries are created. The organization are creating boundaries. First, the organizational boundaries. We have different companies, suppliers, manufacturers, and distributors. And then we have departmental boundaries. We have production department, quality department, maintenance department, procurement department, and so on. And also we have contractual boundaries. Who owns what responsibility? And also we have geographical boundaries, different facilities, different regions, different countries. Okay. Then we do have functional boundaries, including different jobs, roles, and responsibilities. So these boundaries serve important purpose. They clarify responsibilities, they enable specialization, they make large systems manageable, and they allow accountability also. Now, boundaries create risk. That's a fact. Okay. So why boundaries create risk here? We will explore together, and we will also demonstrate with real case examples. Boundaries have a dangerous side effect. Boundaries amplify responsibility, but also they fragment control. That's the reality. And a study shows that 60 to 70% of food safety failure occurred at organizational interface rather than within single organizations. You remember in the previous module when we studied the interface? Today we will dive deeper and we will design also the elimination of risk between boundaries and interfaces. Hazard don't respect organizational boundaries as we studied earlier. Listeria doesn't stop at the wall between departments, right? And allergen don't recognize contract limitations or contact limitations. Time temperature also time temperature abuse doesn't pause during shift change. Research from supply chain literature consistently highlight how organizational boundaries in food supply chains contribute to these interface failures, leading to systematic vulnerabilities. First, let's explore the organizational boundaries, and we will demonstrate with a small organic farm. Let's say a 50-acre organic vegetable farm has invested heavily in food safety. What the farm does well within their boundaries are excellent field practices. They have proper irrigation water, compost manure, and field sanitation. Also, they have proper worker hygiene. They have hand washing sanitations, they have proper training, and they have proper health monitoring. Also, they have clean harvest equipment. They conduct sanitization of the bins and clean cutting the tools. Then they have uh, careful handling during the harvest to minimize the damage. And they conduct rapid cooling. Now, the farmer's boundaries says our responsibility and when products leave our farm gate. That's their boundaries. Well, what happened outside of their gates? Let's assume the farm delivers products to regional distributor. The distributor operates a shared cooler where the distributor does the following. Organics products from their farm is stored next to conventional grown products. Conventional farms have unknown food safety practice and no separation between different suppliers' products at the distributor's facility. So cross contamination happen in the shared storage space at the distributor, the regional distributor facility. Now the boundary blindness here, the farm cannot see and has no control over what happens in the distributor's facility. They assume that we did our part, the product is safe when it leaves here. Well, the result, foodborne illness outbreak happen. Traceback identifies the organic farm as the source. The farm now is shocked. We did everything right. Well, investigation revealed that the contamination didn't originate on the farm. It occurs in distributors' cooler when their clean produce contacted contaminated produce from another farm. The system reality here, the farm's excellent practice were undermined by conditions outside their boundaries. But because they defined their responsibility as ending at the farm's gate, they never asked what happened to our produce after it leaves. What risk is this in distribution, and how can we influence or verify conditions beyond our boundaries? That's the boundary blindness there. So the boundary, which states our farms versus their distributor, created blindness to the system level risk. And food safety doesn't stop at organizational boundaries, but the farm's thinking did that. All right. Now, let's demonstrate with another example in multinational food boundaries. The Now we are still demonstrating the organizational boundary. Uh, let's assume a global food snack company has a rigorous supplier approval system. So their supplier management process within their boundaries include the following. Each ingredient supplier is audited independently. Supplier must meet strict food safety standards. An annual audit verifies compliance, and each supplier is approved separately. Well, their approved suppliers, first, they have flour supplier. It's audited, approved, an excellent track record. Also, they have oil supplier, uh, has been audited, has been approved, and have excellent track record. And also, they have seasoning supplier, which has been audited, approved, and has also excellent track record. Now, the company's boundaries, each supplier is independent, so we audit each one separately. Traditional way, right? Now, what happened? Uh, what they couldn't see here outside their boundary, the seasoning supplier doesn't manufacture spices. They source them from a broker. The flour supplier also source some ingredients from the same broker. The company never asks, where do our suppliers get their ingredients from? Now, the boundary blindness here, the company's audit boundary is stopped at their direct suppliers. Here one, they didn't look upstream to their supplier's supplier, the tier 2 supplier. The results there, the shared broker has a salmonella contamination event, and suddenly two of the company's independent ingredients are contaminated simultaneously. The seasoning contains contaminated spices from the broker, and also the flour contaminated grains from the same broker. So the company is blindsided here. How could two independent suppliers both have salmonella at the same time? Well, the system reality is the suppliers weren't independent. They were they have shared a common upstream source. But because the company's boundary is stopped at tier 1 supplier, they couldn't see the tier 2 connection. One contamination source affected multiple ingredients here because the system extended beyond the company's organizational boundaries. Their independent supplier were connected through a shared broker, but the boundary prevented them from seeing the critical connection. The boundary blindness made them vulnerable to a single point of failure they didn't know existed. Now let's explore the departmental boundaries. Example, a mid-sized dairy processor. For departmental boundaries, a cheese manufacturing plant is organized into three separate departments, each with its own responsibilities and metrics. Okay, so the production department responsibilities is to meet production targets and maintain efficiency. The metrics for production department is units produced per hour and downtime minimized and yield. And their view, equipment is running fine, meeting the production target, that's it. And their boundary is production output and efficiency. That's the production department of the cheese manufacturing plant, okay? Then they have maintenance department. The responsibilities here is preventive maintenance schedule and equipment repairs. Their metrics, scheduled maintenance, completion, and response time to breakdown. And the view of the maintenance department here is completed all scheduled preventive maintenance on time. And the maintenance department boundary is maintenance tasks and schedules. Then the third department is quality assurance department of the same company. The responsibility here is product testing and environmental monitoring and compliance. The metrics for the quality assurance department include test results, audit score, and regulatory compliance. And the view of the quality department here is environmental monitoring shows increasing listeria positive. 3% last month, 5% this month, 3% previous month, 5% last month, and 8% this month. And their boundary here, testing and compliance. Okay, those are three departments from the same company. Now, the boundary blindness here, production sees equipment running, target met, so they don't see the environmental monitoring data. And they say that's a QA job, that's a QA domain, according to the boundaries. So they don't know the listeria is increasing. Then for the maintenance department, maintenance sees all scheduled maintenance completed on time. They don't see the environmental monitoring data, that's QA domain again, so they don't know their maintenance approach is inadequate. Then for the QA department, they see listeria positive increasing. They don't see the equipment condition because that's maintenance domain according to their boundaries. They don't understand the production pressure. That's production's domain as per their boundaries. So the issue report saying enhanced cleaning, but they don't know why cleaning is failing. Now, the system reality here that no one sees. The aging equipment has developed micro crack and hard to clean surfaces over time. This is a maintenance issue, but maintenance schedule tasks don't include detailed equipment inspection for cleanability. They don't check if equipment runs, not if it can be cleaned efficiently. Sorry, they only check if the equipment run, but not if it can be cleaned effectively. The production's cleaning procedures were designed for new equipment, right? But they don't work on aging equipment with crevices. But production doesn't know the equipment condition has changed. Maintenance never told them because it's still running and fine. Well, QA, on the other hand, sees the contamination increasing but doesn't have the authority or expertise to evaluate equipment design. They can only report the problem and recommend enhance the cleaning, which doesn't work because the root cause is equipment condition, not cleaning effort. Now, the results here, the problem cascades for months. Month one, okay, 3% environmental positive. So QA reports enhanced cleaning. They conducted the tests again in the second month, and there is a 5% positive. The production increased the cleaning frequency as per the recommendation from the QA. And then in month three, 8% positive. Now QA issued a report of serious concern. The month four, the finished product tests positive in the finished product. So now crisis happened. In month five, intensive investigation finally discovers equipment crevices. And in month six, the equipment was replaced and the problem is solved. Well, let's see further. Why it took so long? Each equipment operates within its boundary. No one had visibility across all three domains. equipment conditions, plus cleaning effectiveness, plus contamination patterns. The boundaries prevented them from seeing that. Maintenance issue, equipment degradation, created production issue, impossible to clean effectively, which manifested as a QA issues, environmental contamination. By the time they connected the dots across departmental boundaries, months had passed and a recall happened or occurred. The insight here, the problem wasn't that any department was incompetent. Each department was doing its job within its boundary. The problem was that the system level issue, aging equipment creating harbor sites, couldn't be seen from within any single boundary. It only became visible when someone looked across all three departments simultaneously, which didn't happen until a crisis forced it, right? Now let's look at another example, restaurant chain. The fast casual restaurant chain operates with three separate departments, each working with its own boundary. Now we are exploring further the departmental boundaries with another example. So here now in a fast casual restaurant, the departmental boundaries are as following. Corporate Food Safety Department is located at the headquarters. The department, the, they developed a comprehensive allergen management protocol, the Corporate Food Safety Department, which is located at headquarters. And then the protocol has 15 detailed steps, and this protocol requires dedicated cutting board for all three for all allergen-free operations, and it requires also separate preparation area. And this protocol specifies 10 minutes changeover time between allergen and non-allergen orders. Now, the operational department, which manages restaurants' performance, does the following: focuses on customer service and throughput. And during lunch rush, usually they have 200 customers per hour. Okay. And the average order preparation for them, especially during this rush hour, is 3 minutes. So they cannot stop production for 10 minutes without creating massive backlog. And they measure the success, the operation department measures success by speed of service and customer satisfaction. Now, there is a separate department, which is training department, that teaches procedure to staff, the protocol that was issued by the food safety department from the headquarters. What it does, it did receive the 15-step allergen protocol from corporate food safety. So they teach exactly as written during new employees orientation and does not discuss operational constraints or real world challenges. And it assumes if staff are trained, they will follow the procedure. The boundary blindness here, corporate food safety doesn't see or understand the operational reality of a lunch rush. They designs the protocol in an office, not on a restaurant line, serving 200 customers per hour. Operations doesn't communicate back to corporate food safety that the 10 minutes changeover is operationally impossible during peak hours. Assume corporate knows what they are doing. Training teaches the protocol as if it's feasible without addressing the conflict between what the procedure says and what operations demands. The result here, kitchen staff face an impossible situation, follow the 10 minutes protocol, and face angry customer and manager pressure about the slow service, or take shortcuts to keep up with demand and compromise allergen safety. Predictably, staff developed workaround. They use the same cutting board but wipes it very well. They skip some of the 15 steps. They reduce the 10 minutes changeover to 2 minutes. So when an allergen incident occurs, corporate food safety blames staff not following procedure. Operations blame unrealistic food safety requirements. And training blame inadequate supervision. You see the blame culture, how it happened. Now, the system reality here, no one is wrong within their boundaries. Corporate food safety is right that 10 minutes is needed for proper allergen control. Operations is right that 10 minutes is impossible during lunch rush. And training is right that they taught the procedure correctly. But because each department operates within its boundary and doesn't see others' constraints, they created a system where failure is inevitable. The boundaries prevented them from seeing what they needed, a different solution, perhaps a simplified protocol for high volume period or scheduling urgent orders outside peak hours, something like that, or redesigning the kitchen layout to enable faster changeover. The boundary blindness here made an allergen incident predictable, not because anyone was incompetent, but because the system was designed by three departments that couldn't see each other's reality. Now let's explore the process boundary, the process boundaries, okay? We'll start with the example of poultry processor. A chicken processing plant is organized into distinct process steps. Each with its own team has a plan and quality metrics. Step 1, receiving department. The responsibility, accept or reject incoming birds. The checks here, temperature, visual inspection, visual inspection for contamination. The acceptance criteria is temperature below or equals to 40 degrees Fahrenheit and no visible fecal contamination. Their boundary, accept or reject based on our criteria. That's it for receiving department. Then step 2, processing department. The responsibility here, evaporation, washing, and chilling. The checks here, chill tank temperature and final bird temperature. Acceptance criteria for processing department include birds reach 40 degrees Fahrenheit or below within specification time. Their boundary here is to achieve target temperature. Then we have step 3, the further processing department. The responsibilities here is cutting, marinating, and value-added products. The checks here include microbial testing, temperature monitoring. Acceptance criteria include microbial count within specification limit. Their boundary is to meet microbial specifications. Step 4, the packing department. The responsibility, final packing, labeling, and case coding. The checks here, packing integrity, label accuracy, and shelf life rating. Acceptance criteria here include minimum shelf life requirements met, and their boundary, packing meet specifications. That's it. Well, what happened? The system behavior here. A load of chickens, load of chickens arrives at receiving within a slightly elevated temperature, around 42 degree Fahrenheit, and the specification allow up to 45 degree Fahrenheit. Okay. Now the receiving department temperature is 42 degree Fahrenheit within our acceptance limit of 45 degree Fahrenheit. So it's passed. And then to processing's view, you say these birds are harder to chill than usual, taking longer to reach target temperature. But we eventually achieve 40 degree Fahrenheit, so they passed also. Then the further processing's view, they say microbial count are higher than typical. Usually is 1000 CFU per gram, okay? But today is 45,000 CFU per gram. But our specifications allows up to 5,000 CFU per gram, so it's passed. The packing's view here, shelf life testing shows 12 days instead of our typical 14 days. But our minimum requirement is 10 days, so also it passed. The boundary blindness here, each department operating within its boundary sees an acceptable results. Receiving within temperature spec, check. Processing, chill temperature, check. Further processing within microbial limits, check. Packing meets minimum shelf life, also check. But no one sees the system's behavior here. The elevated temperature at receiving cascaded through every subsequent step, degrading quality at each stage, and the cumulative effects created a marginal product that technically passes all checkpoints but fail the market with a shorter shelf life, customer complaints, and quality issue. The system reality here, the problem is not that any single step failed, each met its specification. The problem is that each step only looked within its boundary and couldn't see the following. First, how upstream conditions, the elevated receiving temperature, affected their processes. Secondly, how their marginal performance affected downstream processes. Thirdly, cumulative degradation across the entire system. The boundaries prevented seeing that within specs at each step doesn't guarantee acceptable system outcome. Let's move to the bakery supply chain. Example for the boundaries blindness also. A bakery has a long-standing relationship for, with flour mill. Both parties operate within clear boundaries. All right. Now, the mill's boundaries are the following: responsibilities, deliver flour meeting specifications. Specifications, moisture at 14%, protein between 14 to 13%, and ash under 0.5%, and microbial limits are met. Their view here, if flour meets specs, we done with our job. We done our job. And then the baker's boundary, the responsibility, receive flour meets specification and used in production. The verification they have here, the bakery, include check certification of analysis and visual inspection of the flour. And their view, if flour meets specs, it should work in our process. So what happened? The hidden change here. The mill changed wheat supplier, different growing region, different harvest conditions, and different wheat variety. The new wheat produces flour that still meet all specification. Moisture 14% check, protein 12% check, ash 0.4% check, microbial limits met check. The mill's view here, flour meets specs, no need to notify the bakery. It is the same product. The bakeries experience the following. Week 1, receive new flour, certification of analysis shows all specs met, and production begins. Week 2, bakers notice dough behaves differently. Water absorption, first, absorption is different now because the dough is too dry or too wet sometimes. And then the fermentation time now is different because it rise faster sometimes or slower sometimes. And the dough handling characteristics have changed also. It's more sticky sometimes or more stiff sometimes. Now, in week 3, the quality issues appear. First, inconsistent loaf volume. Secondly, different crust color. Third, texture problem. And fourth, shorter shelf life. Week 4, customer complaint increase. Bakery investigates their process. In the bakery there, right? Because they are the one receiving customer complaint. So they investigate in their process. They check the mixtures setting is unchanged. They verify fermentation temperature is correct. They review the baking time and temperature is all correct, and they test the yeast activity is also normal. Okay, now week 5 to week 6, the bakery adjusts their process, trying to compensate, to eliminate the customer complaint and the quality issue. So they increase or decrease the water, adjust mixing time, modify fermentation time, and change baking parameters. Nothing works consistently. Still, they have the issues. Problem is still there. Week 7, bakery finally contacts the mill. Is something different with the flour? They ask. Week 8, the mill investigates, discovered wheat supplier change. New wheat has different functional properties despite meeting specifications. Now, the boundary blindness here, as we can all see, the mill's boundary meets the specification. That means it's the same product. They didn't see that the functional properties, how flour behave in baking, change even though chemical compositions meet specifications. That's for the mill's boundary. The baker's boundary will say our process must be the problem. That's what they said. They did they didn't consider the flour change because the certification of analysis showed it meets the specifications, right? So they didn't consider that it's from the flour. They check the certificate of analysis, all within the specifications. So they start changing their process there. Now, the system reality here, both parties operated correctly within their boundaries. Mill delivered flour meeting specifications, and bakery received flour meeting specifications. But the boundary prevented seeing the system level change. The flour's functional properties change in ways not captured by specifications. The mill didn't communicate the change because specs were met. The bakery didn't suspect the flour because specifications were met also. The results here, 8 weeks of production problems, quality defects, customer complaints, and wasted products, all because process boundaries prevented seeing that's meet specification doesn't mean functionally equivalent, right? Now we can all understand. Let's explore now the geographic boundaries. Example from fresh produce importer. A US produce importer has diversified their supplier base for risk management, which is correct, right? Diversification for security. Their supplier structure is like this. In Mexico, they have five berry farms um, that supply them from January to April. In Chile, they have four berry farms that supplies them from May to August. And in Peru, they have three berry farms that supply them between September and December. Now, their management approach here within geographic boundaries, each is as following. Each country is managed separately, different regional managers for each country, each farm audited individually, and there is country-specific food safety protocol and independent corrective action systems. That's the management approach within geographical boundaries. Now, their boundaries here, each country is separate, so each farm is independent, and we manage each one individually. What they couldn't see, the hidden connection here, all three countries source irrigation water from rivers affected by the same weather pattern, El Nino, La Nina cycle, all right? The cold and the hot, or the rain seasons and the hot season. So what happened? In year one, El Nino bring heavy rains to all three regions simultaneously. And in Mexico, in January, that supply them from January to April, they have heavy rains cause river flooding, irrigation water contaminated with runoffs, microbial contamination is now in berries has increases, and importer sees Mexico contamination event. That's what the importer see. There is a contamination in Mexico. So they respond, they enhance testing in Mexico and work with Mexican farms on water treatment. All right. Then during the supply season from Chile, which is from May to August, the same weather patterns, heavy rain and river flooding. Again, here in Chile, irrigation water contaminated, microbial contamination in berries increase, and the importer sees Chile contamination event. They respond, enhanced testing in Chile, work with Chilean farms on water treatment. Chilean farms. The Chile are called Chilean. All right. Now, let's move to Peru, where they get the supply between September and December. What happened there? The same weather pattern continue. Heavy rain flowed. Irrigation water contaminated. Microbial contamination in berries increases. And importer sees Peru contamination event. The response here, enhanced testing in Peru, work with Peruvian farms on water treatment. Now, the geographic boundaries blindness here, the important sees three separate independent contamination events in three different countries across 12 months. The system reality here, one weather patterns affecting all three regions simultaneously, creating system-wide contamination risk. Okay? What boundaries prevented them from seeing are the following. First, the contamination event weren't independent. They were connected through shared environmental conditions. The timing wasn't coincidental. It follows a predictable weather pattern. The solution shouldn't be country specific. It should be system wide solution. Now, what they could have done, if they saw across geographical boundaries was going to be the following. They would have done the following. First, monitor El Nino or La Nina forecasts that will predict the risk before it occurs, right? And then implement enhanced testing during rainy season across all regions. That will be a proactive approach, not a reactive. Thirdly, develop alternative water source for all farms, and that will be a system-wide solution. Thirdly, adjust harvest timing across all regions during high-risk period. So that will be a coordinated response. And then share lesson learnings across regions. So what worked in Mexico will be applied in Chile and in Peru. So instead, they treated each event as isolated, implemented country-specific solution, and didn't recognize the system-level pattern until year 3 when the cycle repeated. All right, that's geography, boundaries, blindness, and how to solve it. Now let's examine in seafood distributor. Same geographic boundaries, okay? A seafood distributor operates across 3 U.S. regions. The regional structure is as following. The Northeast region, Boston headquarters, has 8 cold storage facilities and 50 suppliers. Then in Southeast region, the headquarters in Miami have 6 storage facilities and 40 suppliers. Then Gulf Coast region, New Orleans headquarters, has 5 cold storage facilities and 35 suppliers. Now, their management approach is as following. Each region has had independent management, regional P&L responsibilities, profit and losses, and regional supplier relationships, and regional quality systems, and regional corrective actions processes. The boundary here, each region is independent. Regional managers have full authorities. Okay? Now, what happened? The hidden shared dependencies here. All 3 regions use the same third-party logistics provider, 3PL, for temperature control transport, a national company with refrigerated trucks operating in all 3 regions. All right? So, in the first month in Northeast region, what happened? First, temperature abuse incident increase there in Northeast region. This is in month 1. Investigation, supplier didn't pre-cool product properly. Corrective actions require suppliers to document pre-cooling. The regional manager reports here and the problem is solved. That's in month 1. In month 2, in Southeast region, what happened? Temperature abuse incident increase. Investigation, product held too long at duct before loading. Corrective action there, reduce duct holding time. And the regional manager reports and the problem is solved. In month 3, in Gulf Coast region, what happened? Temperature abuse incident increase. Investigation, summer heat affected transport. The corrective action there, adjust delivery schedules to avoid peak heat. And the regional manager reports, and the problem is solved also. Now, the geographic boundary blindness here, each region sees a local problem with a local cause required a local solution. All right? The system reality, the 3PL company deferred refrigeration unit maintenance across their entire fleet for cost-cutting measure. So the refrigeration units are failing in all 3 regions simultaneously, but each region only sees their own incident. Now, What the boundaries prevented them from seeing here? First, the same 3PL operates in all three regions' shared infrastructure. That's a shared infrastructure, right? Secondly, the timing is simultaneous, not coincidental. It's a system-wide cause. Thirdly, local causes are symptoms, not root causes. That's a misdiagnosis there. Fourthly, the local solutions don't address the actual problems. The actual problem is ineffective interventions. Now, what finally uh, revealed the pattern? In month four, corporate quality director happened to attend a meeting with all three regional managers. As a during the casual conversation, the following happened. Northeast manager, we have been having temperature issues. Southeast manager, us too. We thought it was our supplier. Gulf Coast, same here. We blame the summer heat. Well, someone asked, who is your logistics provider? All three, same company. Now, the system reality here, the geographic boundaries prevented seeing the following. First, three independent problems were actually one system level problem. Secondly, the common factor, 3PL, was invisible because each region only saw their segment. Thirdly, months of ineffective corrective actions occurred because the root cause was outside each region's boundary. And fourth, the solution requires corporate level action, change 3PL, or require maintenance verification. The boundaries created blindness to shared infrastructure and system dependencies. Now let's explore the temporal boundaries. And we start with the example of seasonal food manufacturer. A food company produces pumpkin-based products, pies, purees, and seasoning with concentrated production season. Okay, so their production cycle is as following: from September to December, full production 4 months. So they hire 50 season workers, train new workers 2 weeks, run production at full capacity, lay off season workers in December, and then in January to August, it's off season 8 months. They retain only 5 core staff. The equipment are idle there, not in use, and no production activity. All right. Now, their boundary here, each season is independent. We hire, train, use, and start fresh next year. And what happens every year? The repeat patterns is the following. From September, in September, from week one to week two, they have startup problems, which are new workers unfamiliar with equipment issues after 8 months of sitting idle, quality defects during startup, safety incident, cuts, burn, equipment incidents, and production efficiency, only meeting 60% of targets. Then in October, from week 3 to week 6, is the period of learning curve every year. So what happened? Workers gaining experience, equipment issues being resolved, quality improving, safety incident decreasing, production efficiency is rising to 75% of target. And then in November, from week 7 to week 10 is the peak performance. What happened here? Workers now experienced and efficient, equipment running smoothly now, quality consistently good, safety incident rare, and production efficiency is rising to 95% of the target. Then on December, from week 11 to week 14, is where the excellent performance happened. And the following workers are highly skilled at this time, are optimized, quality excellence, safety records are strong, and production efficiency now achieve 100% of target. Then from December 31st, they lay off all the seasonal workers. All the knowledge and experience walk out the door, and equipment shut down again for 8 months. The next September, they repeat the entire cycle again, hire new workers. Most previous workers, of course, by this time have found new jobs. Then start from zero again, same startup problems, same learning curves, same patterns. And the temporal boundary blindness here. The company sees 4 independent production seasons. Each season is a separate project. The system reality, one continuous 12-month system where we deliberately destroy knowledge every year and spend the first 2 months of every season relearning what we knew last year. This is the system reality. What boundary prevents them from seeing this are the following. They, uh, the boundaries prevent them from seeing the following, okay? They lose 2 months of productivity every year to the learning curve. 50% of their production season is lost for the learning curve. And then they repeat the same startup problem every year. Equipment issues, quality defects, and safety incident. And also they invest in training that has zero return after 4 months. And the system never improves year over year because knowledge doesn't accumulate. The cost of temporal blindness here, let's calculate for the 5 years, the cost for their temporal blindness. They have in 5 years, 10 months of 10 months lost to learning curve, 2 months every year multiplied by 5 years, right? And then repeated equipment startup issues, same problems never resolved. Then repeated safety incident, same incident never prevented. And then repeated quality defects, same issue never eliminated. And then training investment with no cumulative benefits. Now, what a system view would do, if they had a system view, they will do the following, okay? We don't have 4 month season. We have a 12-month system with a 4 months production window and an 8 months knowledge retention challenge. That's what the system view would do. And the system level solution will be the following if they have this view. First, retain 15 to 20 core workers instead of 5 year round to maintain the knowledge base. Secondly, use off-season for equipment maintenance and improvement to prevent the startup issues. Then, document lessons learned each season, capture the knowledge, and then create visual training aid and job aid to reduce learning curves. Then, redesign equipment for intuitive operation to reduce training dependencies. Then, cross-train co-workers in other products during off-season to utilize the capacity here, right? The result, if they implemented this, year two startup efficiency will start at 85% versus 60%. And year three will start at 90%, and year two will start at 95 because knowledge accumulate instead of resetting to zero. All right? That's how you solve the temporal boundaries. Let's examine it with the next second example, the food safety audit cycle. Okay, the temporal boundaries again. Another example. A food manufacturing facility operates under annual third-party certification audit. Their audit cycle is a 12-month temporal boundary. So it starts like this. Month 1, January, annual audit. In annual audit months, what they do, third-party audits conduct 2 days audit, findings issued, 3 major non-conformances, 8 minor non-conformances, and then the facility receives audit report. That's in January, okay? In month 1. Then in months 2 to 3, from February to March, corrective actions period from January. So what they do, address all the findings, implement corrective actions, document everything, submit corrective actions report, audit will verify and close, and then the certification is issued, right? Then in month 4 to month 11, from April to November, is the normal operation. So what happened in normal operation? Production focus at this time and gradual drift begins. Documentation become less rigorous from month 5. Shortcut developed under production pressure from month 6. Training becomes less formal in month 7. Cleaning standards slip slightly in month 8. Monitoring becomes less consistent in month 9. Procedures not followed exactly in month 10. And small deviations become normalized in month 11. Then in December, month 12, is pre-audit preparation again. So what happened? Intense focus on compliance and audit readiness activities include catch up on documentation, deep cleaning everything, retrain all staff, review all procedures, verify all monitoring records, fix everything that drifted, and facility looks perfect for audit. It's in December. Then in month 1, January, come back, the audit happened. The auditor finds issues that developed during month 4 to month 7, the drift period. Same type of findings as last year, and the cycle repeats. Now, the temporal boundary blindness here, the facility sees the audit to edit. 12-month cycle. Each audit is independent. We pass audit means success. Okay? The system reality is the facility has pattern of behavior driven by the temporal boundaries, which are the following. From month 1 to month 3 is high compliance audit pressure. From months 4 to 11 is gradual degradation, no immediate accountability. And then from month 12, intense recovery, audit approach. And that repeat and repeat and repeat. So what the boundary prevents them from seeing here are the following. First, getting ready for audit is a symptom of system that doesn't maintain standards continuously. Secondly, the audit doesn't measure actual food safety. It measures, wait, I think I have some issue here. No, wait, I don't know what happened here, but uh, let's go back. We hope we are in the same. Yeah, audit doesn't measure actual food safety. It measures the stage of the facility on audit day. Okay? Now, the standards drift during the 8 months gap between audit pressure points. And the same issue occurs every year because the system conditions that cause drift never change. And they are optimizing for passing audit, not producing safe food continuously. The question the temporal blindness prevents them from asking are the following questions. First, what causes the standards to drift during month 4 to 11? Secondly, why does production pressure override food safety during middle of the cycle? Third, why do we need audit readiness activities if we are maintaining standards continuously? Fifth, why would it take what would it take to maintain month 1 performance for all 12 months? Now, what a system view would see is the following. The annual audit cycle creates a temporal boundary that allows 8 months of drift followed by 1 month of recovery. This pattern indicates the system doesn't have continuous accountability. It has annual accountability. All right. The system level solutions will be the following. First, implement monthly internal audits, shorter feedback loops. Okay. GMP, GWP, and all that. Then make food safety metrics visibility daily. This for continuous accountability. Then change performance metrics. Managers evaluate it on continuous compliance, not audit results. Then implement pair audit between facilities, the ongoing external perspective. Audit A, uh, person from department A audit go to audit department C, and department C come to audit department B, and department B go and audit department A, like that. Okay, this will give ongoing external perspective. Now, then create always audit ready culture by eliminating the concept of getting ready. And also address root causes of drift production pressure, which include production pressure, resources constraint, conflicting priorities. Address those. The insight here, if you need to get ready for an audit, your system is not working continuously, it's working cyclically. The temporal boundary audit to audit creates a rhythm of compliance and drift that annual audit can detect because it only sees 1 day out of 365 days of the year. Food safety doesn't cycle with audit schedule. It operates continuously regardless of when auditors arrive. All right? Now, how boundaries hide risk? First, nobody owns the interface. That's how boundaries are high risk. When responsibility transferred from one party to another, the handover itself often has no clear owners. Both parties manage their side, but the gap between them remain unclear or uncontrolled. Secondly, boundaries hide risks because information doesn't transfer. Critical knowledge about hazards, handling requirements, or problem stays trapped within boundaries. What one party knows doesn't reach the next party when who needs to know. Thirdly, each boundary is defended. When problems occur, boundaries become defensive positions. That's not my responsibility, or it was fine when it left us, and that prevents system level understanding. Also, boundaries hide risk because the end-to-end visibility disappear. No single party sees the complete pathway from farm consumer. Each sees their segment, but the system level risk remains invisible. Real world example, consider temperature control in a cold chain. Supplier controls temperature until product leaves their dock. Logistics control temperature during the transport. Receiver controls temperature after products arrive their dock. Each party has documented control and monitoring. But the 45 minutes between supplier duct and truck or between truck and receiver duct, that interface has no clear owner. Temperature abuse occur in these gaps, not because anyone failed, but because the boundary created blindness. Example of 2008 salmonella outbreak in peanut products. In the widespread 2008 salmonella outbreak linked to peanut products, a critical breakdown occurred at the interface between the ingredient supplier, who was the Peanut Corporation of America, and manufacturers. Despite the supplier's internal HACCP plan, salmonella contaminated peanut were shipped and used in a variety of products. Manufacturers often relied on certificate of analysis from the supplier without independent verification, especially for a low risk ingredient. The boundary between the supplier's responsibility for safe raw material and the manufacturer's responsibility for safe finished products became a blind spot, allowing contaminated ingredients enter the food supply chain and cause illness across multiple estates. So why this explains pattern 3, pattern 2, the interface failure aren't about incompetent people or poor procedures. They are about boundaries necessary for organization, which create a structural blind spot where control break down. The practical diagnostic question here, map your product flow and count how many organizational boundaries it crosses. Each boundary is a potential blind spot. So what this means for design, you cannot eliminate boundaries, they are necessary, but you must design explicit controls for interfaces. Include assign interface ownership, verify information transfer, monitor handover points, build end-to-end visibility, and adapt shared monitoring system as some major retailers now require, where the key data, for example, temperature log during transit, is continuously shared and verified across supplier boundaries to reduce interface risk. So this will bridge to governance, who owns system level accountability, ownership, clarifying responsibility at boundaries, interface, explicit management of handovers. So the power of expanding boundaries with a real example, let's assume a mid-sized food company was experiencing recurring allergen contact issue. Traditional investigation, narrow boundaries will be which production line had uh, the incident? What did the operator do wrong? The system investigation, expanded boundary, they mapped the entire allergen flow through the facility. First, receiving, where allergen enters. Secondly, storage, where allergen are kept. Thirdly, production schedule, which products run when, and then changeover procedures, how lines are cleaned. Then waste handling, where allergen waste goes, and then air handling, how allergen dust moves, and then personal traffic, how people move between allergen and non-allergen areas. By expanding the boundaries to see the whole system, they discovered the following. Um, First, allergen dust from one production line was carried by air handling to a non-allergen line. Okay, then waste bins from allergen production were wheeled through non-allergen areas. Then personnel changed shift between allergen and non-allergen lines without adequate hygiene barriers. Then the production schedule altered allergen and non-allergen production, maximizing changeover risk. Now, none of these factors would be visible within a narrow production line boundary. Expanding the boundary revealed the system level condition creating risk, and their solution redesigned the entire allergen management system, including air handling, traffic patterns, production schedule, waste handling, and the result was zero allergen incident over 3 years, and this is the power of expanding boundaries. See the system, you don't see just the part. Now here we are going to explore the critical understanding, the emergence, when system level behavior cannot be predicted from component analysis. And this is very critical here. First, defining the emergence in complex systems. Emergence is the phenomena where system level properties, such as patterns or behaviors, arise from interactions of systems components, but cannot be predicted or explained by analyzing those components in isolation. Okay, that's the emergence. But in food safety, emergence explains why facilities with all the right controls still experience outbreaks and why problems appear that no individual elements would predict the, the outbreak. Understanding emergence is critical, very critical, because it reveals the fundamental limitation of reductionist approaches to food safety management system that the traditional food management system apply. All right. Now, the theoretical foundations for emergence. Let's explore. Emergence is a defining characteristic of complex adaptive systems that's CAS, extensively documented in system science literature. The key properties of emergence are the following. Let's go through them one by one. First, the irreducibility. All right. Irreducibility means the emergent properties cannot be reduced to component properties. You cannot predict traffic jam by studying individual cars, right? And you cannot predict food safety system failure by studying individual control. That's irreducibility characteristic of the emergence there. Second characteristic is novelty. Novelty means here emergent behaviors are qualitatively different from components behaviors. So as we all know, individual neurons don't think, right? But the brain do. So individual food safety controls don't create safety culture. but organizational systems do. That characteristic of emergence is coherence. In food safety also, right? So emergent patterns maintain themselves over time despite component changes. Now, culture of cutting corners persists even when individual workers change. The pattern is a system property, not an individual property here. The fourth characteristic is dynamism. Emergence properties can appear, okay, and disappear, or transform as system conditions change. A facility can shift from safe to unsafe without any single control failing. The shift emerges from changing interactions. All right? Now, let's explore this real world case study, the 2011 cantaloupe listeria outbreak of Jensen Farms. We have also touched base this in our previous module. This outbreak caused 33 deaths and 147 illnesses, the deadliest foodborne outbreak in modern US history. FDA investigations revealed a textbook example of emergence there, right? The component analysis, what was present? First, washing equipment. They used potato washer. There was a used potato washer there in their washing equipment. Secondly, the cleaning procedure was documented, or the cleaning procedures are documented. And then they have trained personnel, experienced farmers, and they have a storage facility with temperature controls. And also they have distribution system with established channels. The component analysis conclusion here, all necessary elements are present. The system should be safe. That's in component analysis, right? The emergent system behaviors, what actually happened is the following. Catastrophic contamination that killed 33 people. How did this emerge? The deadliest outcome emerged from interactions that created conditions no single component would predict. First interaction, equipment design and production characteristics. So potato washer had dead end pipes. It's designed for soil removal, not pathogen reduction. Then the cantaloupes have nut surface. So unlike smooth potatoes, right? Now, the emergent property here, the pipe trapped cantaloupe debris plus moisture, which created incubation environment for listeria growth. So neither equipment nor product alone predicts this. It emerged from their interaction. Second interaction is economic decisions with microbial ecology. So no chlorine used for cost-saving decisions, as we said earlier. And then listeria present environment from soil that was brought in by the truck traffic that would drive inside the facility. The emergent property here, without antimicrobial, washing spread contamination rather than reducing it. Equipment becomes contamination distribution system themselves. Okay? So neither cost decision nor environmental listeria alone created this. It emerged from their interaction. All right? The third interaction is facility design and operational practice. Now, they had cooling system which created condensation, and cantaloupe is stored in same facility as truck loading dock, and truck brought in fill soil. The emergent property here, condensation dripped into clean cantaloupes, recontaminating them with listeria from soil. So again, no single element predicts this contamination pathway. It emerges from spatial and temporal interactions. The fourth interaction is time and temperature and contamination level. Low level contamination after washing, the improper washing, okay? Then historic time before the distribution took days, and then the temperature fluctuation during the historic time. The emergence property here, contamination amplified from low level that might not cause illness to high level, the deadly one. So the timing and sequence of event created the deadly outcome. Now, the critical insight here, you should you could inspect each component individually and find nothing wrong at all. Okay? Equipment present and functioning, procedures documented, personnel trained and experienced, and facility temperature control. But the system behavior that emerged from their interaction was deadly. This is emergence system level properties that cannot be predicted from component level analysis. Now let's examine theoretical framework, how emergence occurs in food safety systems. Emergence in food safety systems occurs through several mechanisms, and we will go through them one by one. First, multiplicative interactions. When factors multiply rather than add, that means risk factor A, equipment, multiplied by risk factor B, no antimicrobial, multiplied by risk factor C, contaminated environments, equals to emergence risk that's uh, orders of magnitude higher than the sum of individual risk, right? So we have poor equipment design, or the equipment was not designed for this product, and then we didn't add, like in the case study here, they didn't add antimicrobial for the economic purposes, and then the trucks were driving in with the field soil, and that resulted in emergent risk that is orders that's orders of magnitude that is higher than the sum of individual risks. Example, Bluebell Creameries of 2010 to 2015 Listeria outbreak that we touched base also. Aging equipment is factor A, increased harbor site. And then inadequate cleaning, factor B, biofilm formation. And then production pressure, factor C, shorter cleaning time. The emergence outcome here is persistent contamination that survives for more than 5 years and causes 10 illness and 3 deaths. Secondly, let's look at the feed loop amplification. When output feedback to the amplifier input, to amplify input. So from contamination to inadequate cleaning to residual contamination to biofilm formation to harder to clean to more residual contamination to a stronger biofilm. That's the feedback loop amplification there. So the this reinforcing loops creates persistent contamination, an emergence property not predictable from any single cleaning event, right? Thirdly, the threshold effect. When system behavior changes abruptly at critical points. It happened Below threshold, system observe the variability and maintain the safety, right? But when it's above the threshold, system loses resilience and failure cascade. For example, production pressure below threshold, workers maintain safety practices, but above threshold, the production pressure, the shortcuts emerge and safety degrades. That's the threshold effects. Then we have network effects. When interconnections create system-wide patterns. First, individual workers' behavior seems acceptable, but network of workers sharing workaround creates emergence culture of non-compliance. Patterns exist at system level, not individual level there. Then we have temporal dynamics when timing and sequence create outcomes. How? Event A followed by event B will lead to safe outcome, but then event B followed by event A will lead to unsafe outcome. Same event, different sequence, then different emergence, right? Let's connect that to our standard ISO 22000 2018. ISO 22000 2018 implicitly recognizes emergence, though doesn't use the term, but in Clause 4.1, context of the organization requires understanding organization's external and internal issues. Organization should understand its internal and external issues, recognizing that the standard recognizing that system behavior emerged from context, not just from controls. And also in clause 8.5.1.5, hazard assessments requires considering likelihood of occurrence in relation to severity. This is acknowledging that risk emerge from the relationship between factor, not from factor in isolation. And also in clause 9.3, management review, it requires reviewing the status of action from previous management reviews. This also recognizing that system patterns emerge from time and must be monitored at system level. However, ISO 22000 still relies heavily on element-based thinking, PRPs, CCPs, and verifications, and doesn't provide explicit guides for identifying and managing emergence properties. The practical implication here, identifying emergence in your system, let's conduct. Let's explore together. To identify emergence properties in your food safety systems, ask these questions, okay? First, pattern recognition questions. Do problems recur even after fixing individual causes? Do failures occur when everything was done right? Do different people describe the same system issues? Do problems appear during specific conditions, during high production, during staff shortage, during seasonal peak? These patterns indicate emergent system properties, not individual component failures. All right? Then we have interaction analysis question. What happened when control A and control B occur simultaneously? How does factor X change the effectiveness of control Y? And what combination of events create vulnerability? Let's explain with example. Allergen control workers during normal production. Allergen control works, okay? The control works during the normal production, but fail during changeover under time pressure. The failure emerged from the interaction of changeover complexity and time pressure. All right? That's the interaction analysis there. Then you have feedback loop question. You should ask what outputs from our system feed back to influence input. Are there reinforcing loops that amplify problems? Are there balancing loops that maintain stability? Let me demonstrate that with example again. Let's say from positive test results will lead to investigation and investigation will lead to corrective actions and corrective action will lead to improved control. It's a balanced loop, right? But positive test result that lead to retest until negative, that lead to release product, is a reinforcing loop that amplifies risk, right? Threshold question. Identify question in your thresholds, okay? First, at what point does system behavior change qualitatively? What conditions push the system past tripping point? What early warning signals or signs indicate approaching threshold? To explain that with example, assume a facility might handle normal production safety, okay? But when production volume exceed 110% of capacity, safety behavior degrade. So 100%, 110% is the threshold where emergent unsafe behaviors appear. All right. Now, questions to discover the network. First, what information patterns exist beyond formal procedures? Second, ask, how do people actually coordinate work? Thirdly, what shared beliefs or practices exist at group level? To demonstrate that with example, a formal procedure says report all deviations, but emergent group norm is only report serious deviations. This norm is a system property that shapes behavior. All right. Let's explore this case study, persistent listeria as emergent property. Research by Billis, Sullivan, and Weidman in 2011 and 2022 and 2021 food protection trends on listeria in an apple packhouse demonstrates emergence. Okay, so the component analysis, 16 different listeria allelic type found high diversity, and the conclusion there, not a persistent strain problem. The system analysis, same locations repeated positive despite strain diversity. Conclusion here, persistent system conditions. The emergence property, Listeria Harburg emerged from interactions of the following. Forklift stop. The forklift stops created microenvironment. The floor cracks provided protection niches. Moisture accumulation from operations. And then the cleaning frequency is once weekly. And also you have time between cleaning allowed biofilm formation. So none of these factors alone create persistent Harburg. The property emerged from their interaction. This explains why cleaning better, addressing one component, often fails. The emergent property requires changing the interaction patterns. The system intervention. First, increase cleaning frequency. This is how like the system intervenes here to change the temporal dynamics, and applied quarterly powder to specific sites, applied quad powder to specific site to change microenvironment, and removed dead end pipe, which eliminated niche also. The result here eliminated listeria from previous persistent site, and 0 uh, out of 5 tests positive versus the 6 out of 10 that test positive before the intervention. So this worked because it changed the interaction that created the emergent property, not just individual component. Conclusion, managing the emergence. Emergence cannot be eliminated. It is a fundamental property of complex system, but it can be managed following uh, these steps. First, recognize emergence. Look for system-level patterns that cannot be explained by individual components. Then map the interactions. Identify which interactions create emergence property. There are beneficial emergence and harmful emergence. Map those, okay? And then design for emergence. Create systems condition that promote beneficial emergencies, like the safety culture, the continuous improvement. Those are beneficial emergence, and prevent harmful emergence, like persistent contamination and normalization of deviance. Fourth, monitor system level properties. Track patterns, trends, and system behaviors, not just individual control point performance. Right? Fifth, intervene at system level. When emergent problems appear, redesign redesign interactions and system conditions, not just individual elements. The fundamental insight here in complex food safety system, the whole is not just greater than the sum of parts, okay? The whole behaves in ways that cannot be predicted from the parts. This is emergence, and managing it requires system thinking. Those are the key reference we had earlier. Now let's explore the essential concept, the feedback loop. Let's start with the feedback loop, the mechanism by which systems learn, adapt, or fail. Defining the feedback loop in system dynamics. Feedback is the process by which system outputs return to influence system inputs or processes, creating circular causality rather than linear cause effects chain. Again, feedback is the process by which system outputs return to influence system inputs or processes, creating circular causality causality rather than linear cause and effect chain. In food safety systems, feedback loops determine whether problems self-correct, like system learn and improve, or self-amplify, system degrade and fail. Understanding feedback loop structure and dynamics is essential because most food safety failures result not from absence control, but from broken feedback loops that prevent learning and adaptation. The theoretical foundation here for feedback in complex systems, feedback loops are fundamental to system behavior, extensively studied in control theory and also cybernetics and system dynamics. The key concepts, let's start first with circular causality. Unlike linear causality, from A to B and from B to C, feedback created circular. A to B and B to C and C to A, and the circle continue. That's the circular causality, which means first, effects become causes, and system behavior is referential, and past actions influence future conditions, and time delay created dynamic complexity. All right, that's the circular causality. The information flow. Feedback requires information about system state to return to decision point. Sorry, feedback requires information about system state to return to decision point. The reality, the quality, timing, and interpretation of these information determine system behavior. All right. So the quality, timing, and interpretation of these information determine the system behavior. Thirdly, the control action. Feedback information must trigger appropriate responses. Okay? So broken feedback occurs when the following happen. First, information doesn't reach decision makers. Information is ignored or misinterpreted. Response is inadequate or delayed. Response creates unintended consequences. All right? So those are what caused the broken feedback. And then we have system learning. Effective feedback loops enables system to do the following: detect deviation from desired state, diagnose causes of deviations, implement corrections, verify corrections effectiveness, and adapt to changing conditions. Without functional feedback, system cannot learn the repeat failures, right? Now, let's explore real-world study of uh, bluebell creameries listeria outbreak. The bluebell outbreak demonstrates catastrophic feedback loop failure. FDA inspection reports from 483 observation revealed the broken feedback structure. Now let's see the intended feedback loops, how it should work. First, environmental monitoring detects listeria. This is how it should work, okay? Then information flow to management. Then management investigates source. Then corrective actions eliminate source. And then verification confirms effectiveness. And then the system return to safe state. That's how it should work, right? The intended feedback loop. But the actual feedback loop, what happened is the following. First, environmental monitoring detected listeria. That's information generated there. And then information did not systematically flow to production management. Feedback broken. So the positive results were documented but not acted upon. That's information being ignored. And then production continued in contaminated environment. No corrective actions took place. And then finished product tested positive. Now problem amplified. And then the product was released anyway. Feedback completely broken. And then the contamination persisted for more than 5 years. System failed to learn. The feedback loop analysis, broken loop one, from detection to response. Okay? From detection to response. First, the sensor detection, environmental monitoring progress as functional. Okay? Information, positive listeria results generated. Communication, results documented but not communicated to decision makers. Broken. Decision, no investigation or corrective actions. Broken again. Actions, production continued. Broken. And then verification, no verification of corrective actions. Again, broken. Broken loop number two, the product from product to testing. Okay. whole or release. First, the sensor, finished product tested. That was also the sensor is functional there. Then the information, positive listeria results, is generated, but the decision, the product should be held, but it was ignored. The production, then action, the product released to commerce, broken. The consequences, contaminated product reach consumer, system fail. The broken loop number three was illness reported, and then they investigate from the reporting of illness to investigation. First, censored CDC illness surveillance, functional there. They reported, right, the illness. Then information, listeria illness linked to ice cream was generated. Then the communication, reach company, delayed. Then response, recall initiated. Too late, three dead. Three deaths occurred already. The system behavior here, without functional feedback loops, the system could not do the following. First, detect that contamination was occurring. Secondly, learn from positive testing results. Thirdly, correct the contamination source. Fourth, prevent product release. And fifth, protect consumers. This is not a control failure. Control existed. This is feedback failure. Information could not trigger corrective actions. Now, let's look at the feedback loop structure, the technical framework. To analyze feedback loops in food safety system, map these components is first sensor or measurement. What information is collected? That will include either environmental swapping or product testing results or temperature logs or audit findings or customer complaints or illness report. That's the information to be collected, right? Then the quality criteria of the information, accurate. Does measurement reflect the reality? Frequency. How often is information collected? And coverage. What percentage of system is monitored? Secondly, the information flow. How does information reach decision maker? And explore the following: communication channel, formal report, or informal uh, conversation. How does the information reach the decision maker? Is it through time delay, like real time, daily, weekly, monthly? Also explore the information format: raw data, analyze trend, interpretation, or conclusion. And then accessibility: who received the information and who can access it? The failure mode here for information flow: information lost in transmission, information delayed beyond usefulness, information reached wrong people, information overload, signal lost in noise. All right. Now, the third thing is there for the decision or interpretation. How is information interpreted and decision made? Decision criteria. What triggers action? Look for decision authority. Who can act? And then decision speed. How quickly can actions be taken? And decision quality. Are root causes understood? The failure mode here: misinterpretation of data, lack of decision authority, conflicting priorities, safety versus production volume, and inadequate understanding of system dynamics. Action, fourth, action or response. What actions are taken based on information here? Corrective actions fix immediate problems. Preventive actions address root causes. System design, redesign, change conditions that allow problems. The failure modes here: inadequate response, that doesn't address the root cause, or delayed response, the problem amplifies before actions, or no response at all, information being ignored, or wrong response to make the problem worse. Fifthly, conduct the verification. How is response effectiveness confirmed? Follow up monitoring, okay? Or is it trend analysis and also system performance metrics? To confirm the effectiveness through follow up monitoring, trend analysis, system performance metrics, or all. The failure mode here, no verification assume actions worked. If no verification, inadequate verification doesn't detect persistent problems, and delayed verifications problem recur before detection. All right. Now let's apply with the ISO 22000. ISO 22000 explicitly require feedback loop, though often not recognized as such. In clause 8.9, control of management monitoring and measurement requires that monitoring and measurement provide reliable results. This is the sensor component of feedback loop here. In clause 9.1 also, monitoring, measurement, analysis, and evaluation requires analysis and evaluation of appropriate data and information arising from monitoring and measurement. This is the interaction component here. And also in clause 10.1, nonconformity and corrective actions, which requires the following: react to nonconformity, respond, evaluate need for actions to eliminate causes, the root cause analysis here, implement actions, corrective actions here, and review effectiveness of corrective actions also. This is verification here, okay? So this is a complete feedback loop specifications. However, the standards doesn't explicitly address the following: time delay in feedback loops, information flow pathways, decision authority structure, and feedback loops interactions. How multiple loops affect each other. The standard doesn't address those, okay? Now, in clause 10.3, continual improvement, the standard requires that the organization to continually improve the suitability, adequacy, and effectiveness of the food safety management system. This is system level feedback right here, okay? Using performance data to improve the system itself. Let's look at the feedback loop dynamics, time, delays, and system behavior. Time delays in feedback loops creates dynamic complexity and can cause system instability. Short delay example, real-time temperature monitoring. Okay, let's assume the following. Sensor detects temperature deviation, then alarm trigger immediately, then operators adjust the temperature, then system return to control, then feedback loops time is in minutes in this case, right? And the result is stable control. Now, let's look at the long delay example in environmental monitoring. First, the swab collected on day 1, then lab analysis conducted on day 2 to day 3, then results reported on day 4 to day 5, then investigation uh, happened on day 6 to day 7, then corrective actions on day 8 to day 10, then verification swab on day 11, then results on day 14 to 15 for the verification swab. Then the feedback loop time, uh, in this case, took more than 2 weeks, right? Now, the result here, contamination is spread during delay and problem amplified. All right? So the delay problem, when feedback delay exceeds problem development time, the system cannot respond effectively. By the time information triggers action, the problem has evolved beyond the original conditions. All right? Now, let's explore the case example of Peanut Corporation of America. The product tested positive for salmonella in day one. Uh, Instead of investigating, the product was retested again between day 3 to day 5. Then retesting continued until negative result came out in day 7 to day 10. Then the product was released based on negative results in day 11 and contaminated products in commerce in day forward. And then the illness occurred weeks later. Then the outbreak detected months later. Here, the feedback loop delay, months from contamination to outbreak detection, meant the system could not learn and correct in time to prevent death. All right? Now, let's explore the practical tool of feedback loop mapping. For feedback loop mapping, to map feedback loops in your food safety systems, do the following. Step 1, identify critical information. What information is essential for safety decision? First, pathogen test results, then temperature deviations and cleaning verification and supplier audit findings and customer complaints. Step 2, trace information flow. For each information type, where is it generated? Who received it? How quickly? In what form? In what format? And what happened to it? Third step, identify decision point. Where are decisions made based on this information? Who has authority to act? What criteria trigger actions? What actions are available? All right. Then in step 4, map response action. What happened when information indicates a problem? Immediate response to hold the product or stop the production? Investigation, root cause analysis, corrective actions to fix the problem, and preventive actions, prevent recurrence. Then step 5, identify verifications. How is effectiveness confirmed? Follow-up testing, trend monitoring, and performance metrics. Then step 6, calculate loop time. How long from problem occurrence to corrective actions completion? From detection time to communication time to decision time, action time to verification time. Then in step 7, identify broken loops. Where do loops break? Information not collected, or information not communicated, or information ignored, or inadequate response, or no verification. All right? Let's explore this case study, effective feedback loop design. A ready-to-eat meat processor implemented a robust feedback loops for listeria control. The loop design is as following. First, the sensor, daily environmental monitoring of 50 sites, high-risk areas. Secondly, information flow, results enter into database same day, automated alert for positives. Thirdly, decision. Positive results triggers automatic halt of all products from the zone. Fourth, the action include immediate deep cleaning of positive side, investigation of potential product contacts, root cause analysis within 24 hours. Then fifth, the verification, which include re-swap after cleaning same day, trend analysis weekly, Management review monthly. Now, the loop time here 24 48 hours from detection to verification to verified corrective actions. The results here listeria detection rate 2 to 3% of samples indicates sensitive monitoring. Listeria in finished products is 0 over 3 years. No recalls and no illness. Why it works here? Short feedback delay, that's the reason it works, between 24 to 48 hours. And also there is automatic response, no decision delay here. And also authority to act, all product immediately. And also root cause focus, prevent recurrence. And also verification is built in, confirm effectiveness. This demonstrates that well-designed feedback loops enable system learning and continuous improvement. Conclusion, feedback loops as learning mechanism. Feedback loops are how systems learn or fail. To learn, the key principles of feedback loops are as following. First, the feedback must be timely. Delay between problems and response determines whether system can adapt effectively. Second, feedback must reach decision makers. Information without authority to act is useless. Thirdly, feedback must trigger actions. Data collection without response is theater, not management. Fourth, feedback must be verified. Assuming corrective actions worked without verifications allow problem to persist. And fifth, feedback loops interact. Multiple loops in a system affect each other. So it must be designed as a system, not an isolated loops. The fundamental insight here, food safety system fail not because controls don't exist, but because feedback loops that should enable learning and adaptation are broken. Fixing feedback loops is often more important than adding more controls. All right. Now let's explore the essential concepts, balancing and reinforcing loops, the engine of system behavior. Feedback loops come in two fundamental types, and understanding the difference is critical for designing effective loop safety systems, food safety system. Reinforcing loops, growth or decline. That's the meaning of reinforcing loop, okay? Reinforcing loops amplify change. They create exponential growth or exponential decline. All right? Now, food safety examples of reinforcing loops, let's explore them one by one. Positive reinforcing loops, the growth. Good safety performance will lead to management invest more resources, which will lead to better systems, which will lead to even better performance, and which will lead to even more for more investment. Okay, that's a positive reinforcing loop. Growth. This creates a virtuous cycle of improvement. On the other hand, there is a negative reinforcing loop, a decline. Let's explore from a small contamination that would lead to inadequate response, that will lead to contamination spread, which will lead to larger problems, which will lead to overwhelmed response capacity, and that even will lead to more spread of contamination. Right? Now, these create a vicious cycle of deterioration. The critical feature here, reinforcing loops don't self-correct. They accelerate in whatever direction they are moving, either, declining or growth. If left unchecked, they head to either runways, success, or catastrophic failure. All right? Now, let's explore the example one, a small processor, biofilm formation, harmful reinforcing loop here. A small juice processor has a filling line with hard to clean area. The reinforcing loop here is as following. A small amount of product residue remains after cleaning. Then bacteria attack to the residue. Then the bacteria produce biofilm, the protective layer. Then biofilm makes bacteria harder to remove. The next cleaning then leaves more residues because biofilms protects the bacteria. Then more bacteria attack and stronger biofilms is formed now. Then each cycle makes the problem worse. This is a harmful reinforcing loop. It amplifies the problem. The more biofilms you have, the more biofilms you get. How to break it? First, you must interrupt the loop. That's the first thing. Then, redesign equipment to eliminate hard to clean areas, prevent residues. Then, change cleaning chemistry to remove biofilms, to break the protective layer. Then, increase cleaning frequency. Don't allow biofilm formation time. Okay? Then, replace equipment to eliminate the niches. The simple cleaning better, often, that is the practice in traditional way, it fails because the reinforcing loop is stronger than the cleaning efforts. All right? Let's explore the example two. Large facility normalization. Here we will explore the normalization of deviations. Okay? Or the normalization of deviance. Again, harmful reinforcing loop. A large food manufacturing facility has a rule. Stop production if metal detector alarms. That's the rule. Now, the reinforcing loops here goes as following. First, metal detector alarms. False alarm, no metal present. That's a false alarm. Then what happened? Stopping production cost time and money also. So supervisors overrides the alarm to, and allow production to continue. And then no problem happened. That will reinforce the belief that the alarm was false. Next time, when alarm sounds, override seems justified in this case. So overriding becomes normal practice now. And eventually, real metal contamination occur, but alarm is overridden. So product with metal rich consumers. This is a normalization of deviance, a reinforcing loop where each deviation makes the next deviation easier. The more you deviate, the more normal deviations become. So, how to break this? Remove override authority completely. Okay? So it can continue the loop here. Then make every alarm investigation mandatory. Break the no problem occur reinforcement here. Okay? Then change the metrics. Supervisors will be evaluated on zero override, not production volume anymore. So change what's reinforcing action. And then reduce false alarm. Address root cause of the loops trigger. Okay, that's how you break it. Let's explore the third example, farm. Pest infestation, harmful reinforcing loop here. A grain storage facility has a small rodent problems. The reinforcing loops goes as following. First, rodents present eating stored grain. Then rodent populations grow, reproduction. Then more rodents eat more grains, creating more entry points. Then more entry points allow more rodents to enter. The larger population reproduces faster, of course, and then the problem, of course, accelerate. This is exponential growth, a reinforcing loop. The more rodents you have, the faster the population grows. Here, why doing something about it here is not enough? If you reduce the population by 50% but don't break the loop to eliminate the food source and seal the entry point and eliminate the harbor, the population will just grow back, often faster than before because now the sources are now less constrained. Okay? So how to break this loop? First, eliminate food source. Remove what sustains the loop first. Then seal entry point. Prevent loop from continuing. Then eliminate harbor. Remove breeding sites. Then reduce the population after breaking the reinforcing mechanism. So this is why pest control requires system change and not just trapping and poisoning as in conventional way. Okay, this is how you break the loop. Let's explore the fourth example: distributor reputation is a spiral. It can be positive, it can be negative loop here, reinforcing loop. Okay. Now, a food distributor's reputation creates a reinforcing loop. Let's look first at the positive spiral. First, delivery safe, then the quality, uh, safe delivery, and with the quality product. Then customers trust you and they give you more business also, like by the word of mouth or buying more and even doing free marketing for you. That means more business equals to more resources for more quality and more safety system. And now you have better system and even safe that will lead you to better system and even safer and higher quality product. And the reputation there will improve faster and faster. So even more business will grow. You have more customer, you produce more quality, you give more safety, and more customer will trust you, and they will bring more customers. So the even business become more. Now let's look at the negative spiral here. First, one food safety incident. Start with that. Then customer lose trust, and now reduce orders. So less revenue equals to fewer sources for quality and safety. So the system degrade. More incident happen now. So the reputation worsen. And even, now is giving you less business. So this is reinforcing loop that can spiral either direction. The key insight here, once a negative spiral starts, it's hard to stop because each turn makes the next turn worse. How to prevent the negative spiral here? First, invest in safety before incident. Build in positive spiral from the beginning. Then respond aggressively to first incident to prevent a spiral from happening. And then maintain safety investment even during downturn. Don't let resources reduction trigger the negative loops. Okay? That's how you break the negative loop. Now, let's explore the example 5 of manufacturer, the continuous improvement, beneficial reinforcing loop here. Food manufacturer implements a learning culture. The reinforcing loops goes as following. First, encourage employees to report near miss and concerns. Then investigate and fix issues before they become problems. Then employees see their input creates positive change. Trust increase at this point, and employees report more concerns, and more issues are fixed. So the system is improving here, and the success reinforces the culture at this point, and even more engagement and improvement happen. Now, this is a beneficial reinforcing loop. It amplifies improvement. The more you improve, the more you can improve. How to create this loop from the beginning? First, make reporting safe. No blame at all. Cut that off. Then act on reports visibly. Show that show that input matter. So when they report, just fix the problem. All right. And then celebrate learning. Reinforce the behavior. Celebrate those who reinforce who report the problems. Then share the success, which will amplify the positive loops. All right. That's how you create it. And this is why safety culture is a reinforcing loop. Once established, it becomes self sustaining and amplifying. Now, let's look at the balancing loops here, the stability and control. Balancing loops resist change. They seek equilibrium, maintaining stability around a target. Now, let's look at the food safety examples of balancing loops. The temperature control. Let's start with the temperature rises, for example, then the cooling system is activated, then the temperature drop, then the system deactivated, the cooling system deactivated, and then the temperature is stable at this point. Okay. In example of inventory management, stock depletes, that will lead to order replaced, that will lead to stock replenish, then will lead to order stop, that will lead to stock stable. All right. The critical feature here, balancing loops self-correct. They automatically adjust to maintain a target state. All right. Now, let's explore with examples. Small farm, temperature control. A small dairy farm has a walk-in cooler for storing milk before pickup. The balancing loops goes as following. First, desired state is milk at 38 degrees Fahrenheit. The actual state, temperature sensor reads current temperature. The gap here, if temperature rises to 40 degrees Fahrenheit, the gap here equals to 2 degrees Fahrenheit. The action, compressor runs to cool it. And the result, temperature drops back to 38 degrees Fahrenheit. And the gap closes and the compressor shuts off. This is a balancing loop. It maintains stability. The system seeks the goal of 38 degrees Fahrenheit and corrects deviation. Now, what happens if the loop breaks? The following will happen. First, sensor fails, can detect the gap. So the temperature rises undetected. Then compressor fails, can take action. So the temperature rises despite detection. Then alarm doesn't notify farmer. That means information doesn't reach decision maker. The temperature rises without response. Now, understanding this as a balancing loop helps diagnose failure. Which part of the loops break? Second example, light manufacturing, pathogen control. A ready-to-eat meat processor has an environmental monitoring program for listeria. The balancing loops here is as following. First, desire a new state, zero listeria in production environment. Second, actual state, daily swab test for listeria. The gap, positive swab detected. The gap here, preserve versus absence. Okay? And the action here, deep cleaning, investigation, and corrective action. Result, listeria eliminated from that side. The gap closes and the subsequent swap is negative. This balancing loop maintains environmental control. When listeria appear, deviation from desired state, the system corrected. Now, why this loop often fail? Long delay. Swap on Monday, results on Tuesday. That's 4 days delay means listeria spread before action. And the weak action here, enhanced cleaning. That doesn't address the root cause. The action doesn't close the gap. And no verification, which assume cleaning worked without re-swapping, don't confirm gap closed. A strong balancing loop requires fast detection plus effective action plus verification. All right? Example 3, restaurant chain, uh, food cost control. A restaurant chain monitors food cost uh, percentage. The target is 30% of sales. Now, the balancing loops is the following. The desired state is 30% food cost. The actual state, monthly financial report, which shows actual cost, food cost. The gap here, food cost rises to 33%, for example, 3% gap rise. The action, reduce portion size or negotiate supplier's price to reduce waste. The result here, food cost drops back to 30%. The gap closes and the system returns to target. This is a balancing loop maintaining financial stability. Let's explore the food safety implication here. If food cost pressure becomes too strong, it can override food safety balancing loops. If pressure to reduce waste, then holding product longer will lead to temperature abuse. Then pressure to reduce costs, which will lead to cheaper suppliers, which will lead to no wait. Let's start again. The broken loop here. First, a pressure to reduce waste will lead to holding pressure product longer, which will lead to temperature abuse, and then pressure to reduce cost will lead to cheaper supplier, which will lead to quality or safety issues, and pressure to reduce labor will lead to understaffing, which will lead to shortcuts. So understanding competing balancing loops helps explain why everyone knows the right thing to do but doesn't always do it. They are responding to a different balancing loop. Cost control, that's stronger than the safety loop. Okay? Why both matters in food safety here? First, you need balancing loops for the following. maintaining critical parameters, temperature, pH, and time, keeping processing within specifications, stabilizing operations, and preventing drift from standards. And also you need reinforcing loops for the following: building capabilities over time, accelerating improvement, and creating momentum for change and scaling success. The danger, unintended loops here. Many food safety failure involve unintended reinforcing loops. Example one, normalization of deviance. Let's say a small deviation happen, which will lead to no consequences. Then the deviation seems acceptable at this point, which will lead to larger deviation, and still, if there is still no consequences, that will lead to deviation becomes a normal. And from there, even will lead to larger deviation. This is a reinforcing loop drives decline. It accelerates until catastrophic failure. Example, reporting decline. Let's say the problem reported, but the reporter was blamed, so the reporting decreases, and now problems are hidden, and that will lead to more blame when discovered that the problem are hidden, which will lead even to less reporting. Now this is a reinforcing loop destroying your sensing capability. Design implication here. To prevent decline, first identify reinforcing loops that drive deterioration. Then insert balancing mechanisms that stop the acceleration. Then create consequences that break the reinforcing patterns. To accelerate improvement, first identify reinforcing loops that drive improvement. Then remove barriers that slow the acceleration, that amplify the factors that strengthen the loop. Recognizing loop types in your organization. First, let's look at the balancing loops indicators. One, problem appears, get fixed, and then it stayed fixed. That's stability indicator. Those are the balancing loops indicator we are looking at. Then, secondly, system return to normal after this disturbance. Then, consistent performance over time. And also the example for that will be temperature control, inventory management, and quality specifications. The reinforcing loops indicators include problem get worse over time despite efforts, small issues become big issues, success breed more success or failure breed more failure, an exponential growth or exponential decline. Example, biofilm formation, normalization of deviance, repetition effects, and pest reinforcement. If we look at the critical differences here, the balancing loops, you can fix them by strengthening the corrective actions. The reinforcing loops, you must break the loop or it will overpower your efforts. Practical applications here. When you face recurring problems, ask the following: is this a balancing loop that's broken? Then fix the feedback mechanism. Is this a reinforcing loop that's amplifying? Then you need to break the loops and don't just push harder. Example, persistent Listeria contamination. If it's a broken balancing loop, fix detection or actions or verification. If it's a reinforcing loop biofilm, you must break the loop, redesign equipment, change chemistry, and eliminate niches. Enhanced cleaning alone won't work because the reinforcing loop is stronger than your cleaning efforts. Practical applications here. When you see a problem that's getting worse despite your efforts, ask, is this a reinforcing loop accelerating decline? What's amplifying the problem? Where can we insert a balancing mechanism? And when you see improvements that's stalling, ask, is this a balancing loop resisting change? What's pulling us back to the old equilibrium? How can we shift the target or create a reinforcing loop? Connection to Module 3, Pattern 1, slow failure. Here, reinforcing loop of normalization. Pattern 4, symbolic evidence, balancing loop, broken, and evidence no longer trigger connection. Pattern 5, pressure wins, reinforcing loop of shortcuts under pressure. Now, this prepare you for designing monitoring that creates effective balancing loops, building improvement system that reinforces loop towards safety, and recognizing when your system is accelerating toward failure. Now, let's look at the invisible enemy here. Our invisible enemy here is a delay. Delay explains why people misjudge cause and effect and why food safety systems fail to learn from experience. The problem with delay in food systems, actions and consequences are separated in time. First, today's cleaning shortcuts won't show up in this week's tests. This month's equipment maintenance affects next quarter's performance. This season's suppliers' issues create next year's recall. And today's training gaps manifest in future incidents, right? Now, when consequences arrive weeks or months after their causes, the connections become invisible. For that reason, research consistently shows significant time lag in food safety systems. The average time from a contamination event to outbreak detection is often between 28 to 45 days, making root cause identification extremely difficult. This extended delay allows contamination to spread widely before it's even recognized. Let's demonstrate with example. A small bakery, ingredients quality delay. Let's assume a small artisan bakery orders flour from a regional mill. The mill changes wheat supplier, different growing region, right? The timeline here, week 1, mill processes new wheat and ships the flour. Flour composition change. Second week, bakery receives flour, used it in production. No immediate problem visible there. Thirdly, bread quality issues appear. Different rise, different texture, and different shelf life. Then week 4, customer complaints increase, stale bread or quality defect. Then week 5, bakery investigates their processes. They're adjusting their time and temperature and water. Then week 6, bakery contacts mill about flour quality. Then in week 7, The mill investigates and discovers wheat supplier change. And in week 8, solution identified. Just flour specification or change supplier. Well, the delay problem here, 8 weeks from cause, wheat supplier change, to solution. During this time, the following happened. Hundreds of loaves produced with quality issues. Customer trust is damaged at this point. Revenue are lost, and bakery wasted time troubleshooting their process. Wrong target. So why delay created the problems here? Bakery couldn't contact flour change week 1 with quality problem, week 3, because the delay broke the mental connection. They assume their process change, not the ingredient. Okay? That's the danger of delay there. Let's demonstrate with the second example. Mid-side processor, sanitization effectiveness delay. Let's assume a meat processing plant implement a new sanitation chemicals. The timeline, day 1, new chemical is used, surfaces appear clean through visual assessment, looks good. Then day 2 to day 7, production continues, no obvious problems. Then day 8 to day 14, environmental monitoring swab is collected. Routine is scheduled here. And then day 15 to day 17, lab analysis came came back. They have 3 days turnaround. Then the day 18, the results shows increased microbial count. Problem is detected in day 18. Day 19 to day 20, investigation begins. The wheat has changed. Now, day 21, that's when the realization of new chemical is less effective. The cause has been identified here in day 21. In day 22, return to previous chemical. The solution is implemented in day 22. Now, the delay problem here, 22 days from cause, the chemical change, to solution. And during this time, the following happened. Product produced in suboptimal sanitization conditions. Microbial contamination increased and risk to consumer elevated. So why delay created the problem? The sanitization team saw clean surface in day 1 and concluded the chemical worked. The 18-day delay before getting microbial data meant they couldn't learn that look clean doesn't equal to microbiologically clean. And by the time they learned, weeks of production were affected. That's the danger of delay there also. Now, let's examine with the third example. In light manufacturer, equipment degradation delay. Let's assume a large food manufacturer has aging processing equipment. The timeline here, between first and 6 months, equipment developed micro cracks, not visible, and it's not immediate impact. There is no immediate impact there. And then from 7 to 12 months, from month 7 to month 12, the cracks harbor bacteria. The biofilm begins the formation there and not yet detected by routine cleaning. Then from month 13 to month 18, environmental monitoring shows occasional positive, and they attributed that to random contamination. Then in months 19 to months 24, the positive results increase in frequency. Now, the pattern emerging but not recognized from where. Then in month 25, the finished product tested positive. Now that's a crisis happened there in month 25. In month 26, intensive investigation was conducted. Equipment were dismantled and crack was discovered in month 26. And then in month 27, equipment was replaced, the solution. The delay problem here, 27 months from cause, the equipment degradation, the solution. During this time, the following happened. Contamination risk is steadily increased, multiple corrective actions implemented, enhanced cleaning, chemical change, that didn't address the root cause. The resources were wasted on ineffective interventions. So, why delay created the problem here? The 25 months delay between equipment degradation from month 1 and finished product contamination month 25 meant no one connected them from month 1 to month 25. And each environmental positive was treated as an isolated event, not as a signal of progressive equipment failure. Now, let's explore why delay is dangerous. First, the memory fade. By the time consequences appear, people have forgotten what caused them. People will say things like, "We didn't do anything different," because the common refrain, "No, we didn't do anything different," becomes the common refrain because the relevant actions happened months ago. Secondly, the delay is dangerous because the urgency disappears. Problems that won't manifest for weeks don't trigger immediate concerns. Today's deadline always feels more urgent than the next month, than the next month's potential problem. Thirdly, delay is dangerous because the learning breaks down. We learn best from immediate feedback. When feedback is delayed, we can connect actions to outcomes, so we can learn what works and what doesn't. Fourth, accountability weaken. That's another reason of delay is dangerous. When problems appear long after their causes, it's nearly impossible to assign responsibility. Everyone can truthfully say, "That's not what I did," because they are thinking of recent actions, not the relevant past. All right? Now, the longer the delay between cause and effect, the weaker accountability becomes. You need to keep that in mind. Now, there was a note from Peter Senge, the fifth discipline. Delays are often overlooked, but they are omnipresent in dynamic systems and almost always lead to oscillations, instability, or even breakdown. Let's look at information delay examples. Let's start with small farms. Let's assume a vegetable farm sends produce to a distributor. The distributor's cooler malfunction, product's temperature abuse. All right. Now, in day 1, the temperature abuse occurs. Day 5, product reached retail. Day 8, consumer purchases and consumes. Day 10, consumer become ill. Day 12, consumers sees doctor. And day 15, the doctor reports to health department. And day 20, health department traces back to farm. And day 15, farm learned their product caused illness. The information delay here is 25 days, and by the time the farm learned, they have shipped 5 more loads under the same conditions. The delay prevents learning and corrections. Let's give another example in a large manufacturer. A snack food manufacturer has a supplier quality issue. In week 1, supplier has contamination event. Manufacturer doesn't know there. Week 2, contaminated ingredients are shipped. Manufacturer still doesn't know. Week 3, ingredients received and used in production, and manufacturer still doesn't know there. And week 4, the product is distributed. Manufacturer still doesn't know. Week 6, illness occur. Manufacturer still doesn't know. And week 8, outbreak detected by CDC. Manufacturer still doesn't know. And week 10, the traceback identifies manufacturer. Now manufacturers learn at this point at week 5. The information delay here is 10 weeks. Thousands of units produced and distributed before manufacturer learn of the problem. Let's look at the response delay example. Restaurant chain. Assume a restaurant chain identifies a food safety issues in their procedures. Week 1, corporate food safety identifies issue and developed a new procedure. Week 2, procedure sent to regional manufacturers for review. Week 3, regional managers send to restaurant managers. Week 4, restaurant managers schedule training. Week 5 to 6, the training was conducted 2 weeks to reach all shifts. And week 7, new procedures implemented. Now, the response delay here is 7 weeks from identification to implementation. During this time, the unsafe practice continued at least at 200 locations. Let's look at the distributor example. A food distributor discovers a refrigeration problem in one warehouse. Day 1, problem identified, compressor failing. Day 2, maintenance work order was created. Day 5, parts are ordered for 3 days. That will take 3 days to arrive. And day 10, the parts arrived. 5 days shipping. And day 12, the maintenance is scheduled. 2 days delay for technical availability. And day 13, the repair was completed. The response delay here is 13 days. During this time, product in that warehouse is at risk. The delay between identification and repair creates extended exposure. All right. Let's look at the feedback delay example here. Bakery example. Assume a bakery changing their cleaning procedure. So week 1, new procedure implemented. Week 2 to week 4, pairs to be working, visual assessment. And then week 5, environmental monitoring conducted, monthly schedule here. And then in week 6, the results shows increased microbial count. Feedback is received at week 6. The feedback delay here is 6 weeks. The bakery operated for 6 weeks thinking the new procedure worked. When it was less effective. The delay prevented timely correction at this point, right? That's the feedback delay. In seafood processor example, assume a seafood processor adjusts their freezing process to improve efficiency. So in month 1, the process change implemented. Months 2 to 3, production continued, no obvious problem. Month 4, product reaches end of shelf life. And month 5, retailers report quality issue, texture, and drip loss. And month 6, the processor receives feedback. Here, the feedback delay 6 months. By the time they learn the process changed degraded quality, they have produced 6 months of suboptimal product. Real world example environmental monitoring drift. Month 1 cleaning procedure are shortened by 5 minutes due to production pressure. Month 2 no immediate consequences. Pressure remains and shortcuts continue. Month 4 environmental monitoring detect a slightly elevated count attributed to raw materials variation at this point. And month 6, positive findings increase and investigation begins. And in month 7, the root causes investigation tries to identify what changed, but nobody connects it to cleaning shortcut from 6 months ago. The delay uh, made the connection invisible here. The cause, shortened cleaning, and effect, contamination, was separated by so much time that learning couldn't occur. A stark example in the 2011 Listeria uh, outbreak linked to cantaloupe. The initial contamination event at the packing facility likely occurred months before the first illness were reported, and the outbreak was detected, making it incredibly challenging to pinpoint the exact source and implement timely correct actions. Let's explore the delay trap now. Why delay cause overreaction? When feedback is delayed, people often overreact because they can't see the effects of their actions. Example for the delay trap is temperature control with delay. For example, cold storage facility has a temperature control system with a 30-minute delay between compressor activation and temperature change. Large space and slow air circulation. Now, the temperature rises to 40 degree Fahrenheit above target of 35 degree Fahrenheit. Then operator increases compressor power and 10 minutes later, no change visible, delay. And operator increase power more, 20 minutes later, still no change, another delay. Operator increases power to the maximum at this point, and 30 minutes later, the temperature dropped rapidly. And 40 minutes later, temperature at 30 degrees Fahrenheit. That's overreaction there. Now, the temperature is too low. The operator reduces power and cycle repeats. That's oscillation. The delay trap here, the operator can't see the effect of their action. So they keep adjusting and each adjustment is based on old information, leading to overreaction and instability. The solution here, understand the delay, wait for feedback before making additional adjustments. Now, how delay enables Module 3 patterns, the patterns that we studied in Module 3. The first pattern, slow failure, delay allow gradual deterioration to normalize. The consequences arrive too late to prevent harm. And pattern 2 is enabled here, problem move forward. Delay means problems that should be caught early don't show consequences until they are downstream. Pattern 5, pressure wins. Delay means shortcut under pressure don't produce immediate consequences, reinforcing the behavior. Now let's look at the leading versus lagging indicators, bridging the delay gaps. The leading indicators here, proactive measures that predict future performance and allow for intervention before problem occur include HACCP compliance check, environmental swapping frequency, and employees training completion rates. The lagging indicators, reactive measures that assess past performance and confirm whether goals have been met after an event has occurred, include customer complaints, recall events, outbreak investigation, and final product testing results. Now, what time meant for design here? You must design system that shorten delay to get feedback as close to action as possible. Also, you must design system that create memory, document connections between actions and delayed consequences, and then design system that anticipate consequences. Use predictive indicators, not just lagging outcomes. And also design system that maintain visibility, track actions and outcomes over time to reveal patterns, and then design system that map delays, create a delay map showing the time lag between each action and its measurable consequences in your system. Identify critical point for investigation. Managing delay in your operations. First, identify critical delay. Map the time from problem occurrence to detection, detection to decision, decision to action, and action to verification. Example in a small processor, from contamination occurrence, 7 days to environmental monitoring detection. Detection, 3 days to lab results. Results, 2 days to management review. Review, 1 days to corrective actions. And actions, 7 days to verification and swap. And verification swap, 3 days to lab results. The total of 23 days from contamination to confirm corrections. Second, reduce delay where possible. Faster testing methods like ATP instead of cultural 15 minutes versus 3 days. ATP is way better in 5 minutes, right? And then real-time monitoring also. Continuous temperature versus daily log. Implement that. Reduce the delay. Also, automated alert, immediate notifications versus weekly report. And then decision authority. Empower frontliners to take actions versus escalation to management in critical points. Now, thirdly, count for delay. You can eliminate. Don't make multiple changes rapidly. Just wait for feedback. Then use leading indicators, predict problems before they occur, and build efforts. Hold product until verification complete, and communicate delay. Everyone understands the time lag. Fourthly, recognize delay patterns. Recurring problems with log gaps between occurrences, delay breaks the connections. Overreactions and oscillations are just before seeing the effects, and surprise problems delay prevents early warnings. The key insights here, delay doesn't just slow down your response, it fundamentally changes system behavior. It breaks the connections between cause and effects, prevents learning, cause overreaction, and allow problems to amplify before detection. So understanding delay in your system critical for the following. For designing effective feedback loops, minimizing delay, and interpreting system behaviors which account for delay, and avoiding overreaction and wait for the feedback, and preventing problems. You will be able to use leading indicators to overcome delays. So this prepares for traceability, connection cause to effects across time that we will go through, crisis response, understanding that today's problem have historical causes, and also recall logic, backward investigation across delays. And also for leading indicators, sensing problems before consequences manifest. The strategic insights here, let's discover the strategic insight. Leveraging points, where a small change produce disproportionate effects. Let's dive deeper here in leveraging points. Defining the leveraging point in the system dynamics before we proceed. Leveraging points are places within a complex system where a small shift in one element can produce large changes in system behavior. The concept was rigorously developed by system science Daniela Meadows in her seminal of 1999 essay, Leveraging Point Places to Intervene in a System. So, understanding leveraging point is crucial for food safety because it reveals why some interventions produce transformative improvements while others, despite significant efforts and resources, produce minimal change. So, most food safety interventions target low leverage point, the parameters or buffers, while ignoring high leverage points, feedback loops, and system goals and paradigms. We will discover now the 12 uh, leveraging points so that you know which one to target. All right. Now, Meadows leveraging points hierarchy from least most effective, from least to most effective. The Meadows identified 12 leveraging points ranked from least effective number 12 to most effective number 1. So understanding these hierarchies prevent wasting resources on low leverage interventions. First, the low leverage, least effective. We have number 12, the constant parameter and numbers. Example, in food safety, increasing testing frequency from weekly to daily, changing critical limits from 165 degree Fahrenheit to 170 degree Fahrenheit, adding more CCPs to HACCP plans, and increasing audit frequency. Why those are leveraging points? Changing parameters within existing system structure doesn't change how system behave. Example, Bluebell Creameries had extensive testing parameters, but broken feedback loops meant testing results didn't trigger corrective actions. More testing, parameter change, wouldn't fix broken feedback structure problem. That's why this is a low leverage point. Number 11, we have buffer, which is a leveraging point, the size of stabilizing stock. Example in food safety for buffer include increasing inventory to allow longer holding time, adding redundant equipment, and increasing staff numbers. Why this is a low leverage point, buffers can observe variability but don't change system dynamics. All right, example for that, adding more cold storage buffer doesn't prevent temperature abuse if monitoring and response systems are inadequate. The third leveraging point, number 10, is the structure of material stock and flows. Example in food safety for structure of material stock and flow include redesigning facility layout to improve flow, separating raw and ready-to-eat zone physically, and installing barriers between processing areas. So why this is a moderate leverage? Physical structure, physical structure constrains behavior, but doesn't determine it. Example here, the zone separation structure helps prevent cross-contamination, but only if personnel follows traffic patterns behavior. In case of Jensen farms, uh, they had physical separation, but operational practices, as we went through earlier, the truck traffic and contamination, create contamination pathways anyways, right? Now, those are the low uh, leverage points, the low effects. Now let's move to moderate leverage points. Number 9 is the length of delay relative to rate of system change. Example in food safety include reducing lab turnaround time from 5 days to 24 hours, implementing real-time temperature monitoring versus daily log review, and rapid pathogen detection methods versus traditional culture. Now, why this is moderate high leverage? Delay determine whether feedback loops can stabilize system. Long delay means problems amplify before corrections. So example here, in the Peanut Corporation of America case study that we have, they had 3 to 5 days test delays, allowing contaminated product to ship before result return. Reducing delay to 24 hours would have prevented contaminated product release. Then we have number 8 is the strength of negative feedback loop. Example in food safety here for the strengths of negative feedback loops. We have automatic production stop when CCP deviation detected. That's a strong feedback. And also we have weekly review of deviation, weekly feedback, and we have real-time alert versus monthly reporting. Those are the example of strengths of negative feedback loops in food safety. Now, why those are high leverage? The strong feedback loops stabilize system by quickly correcting deviations, right? Example, a processor implemented automatic line stop when metal detector alarm. This strong feedback loop immediate response prevented metal contamination from reaching consumers. The previous system's operator decision to stop was weak feedback. Operator sometimes continue production to finish the batch. All right. Now let's explore number 7, which is gain around driving positive feedback loops. Example in food safety for gain around driving positive feedback loops include limiting production pressure that amplifies shortcuts, controlling growth of contamination, positive feedback that will lead to more bacteria, and more bacteria will lead to more contamination, and more contamination to more bacteria. So we need to limit the control of the contamination there. And then we have managing normalization of deviance. That means positive feedback. One shortcut will lead to other, will follow the more shortcut, become normal. All right. So we need to manage that. So why this is high leverage here? Why those examples are high leverage? The positive feedback loops amplify change, either beneficial or harmful. So controlling their gain prevent runaway problems. Example here, in Jack the Coster egg outbreak that we touched base earlier, rodent infestation created positive feedback. More rodent will lead to more contamination, and more contamination will lead to more feed contamination, which will lead to more rodent, and the cycle continue, right? So breaking this loop, the rodent control would have prevented outbreak amplification. Now let's explore the high leverage, the most effective points. We have number 6, structure of information. Example in food safety for the structure of information flow include who received test results, when, in what format, and making food safety data visible to all employees versus management only, and also sharing audit findings across facilities versus keeping them in silos. Now, why is this high leverage point? Because information structure determines what people know and when they know it, which determines what actions they can take. Now, example here, in Bluebell's critical failure was information structure. Positive test results existed but didn't flow to people with authority to stop production. So Restructuring information flow positive results immediately to production management with stop authority would have prevented the outbreak. The fifth rule is the fifth point, leverage point, is the rule of the system. Example in food safety for the rules of the system include regulatory requirement, food safety management system, HACCP regulations, and company policies such as zero tolerance for pathogens versus acceptable limits. And then incentive structure, such as bonuses based on production volume versus bonuses based on safety metrics. Now, why this is high leverage point? Because rules define what's allowed, what's required, and what's forbidden. And changing rules change behaviors. Example, Food Safety Management System Preventive Controls Rule 2015. No, FSMA Preventive Controls Rules 2015 change food safety from reactive response to contamination, to containment, sorry, from response to containment to reactive, proactive. Let me go back again. The example, okay? FSMA, the American Standard, right? Preventive Controls Rules 2015 change food safety from reactive, from response to contamination, to proactive, to prevent contamination. These rules change transformed industry behavior more than decades of guidance documents, especially in the US, right? Then we have the fourth point, which is power to add, power to change, and power to evolve or self-organized system structure. Example for this point in food safety include empowering frontline workers to stop production when they see safety risk, creating cross-functional food safety team with authority to redesign processes, and allowing facility to adapt HACCP plans to local conditions versus rigid corporate templates, like what we saw there with that restaurant example. Now, why this is a high leverage point? Self-organizations allow systems to adapt to changing conditions. Example here in Toyota's Anadon port system, which means any worker can stop production uh, line, is a self-organization. It distributes decision authority and allows rapid response to problems. So, food facilities that empower workers to stop production when safety is at risk have fewer recalls than those requiring management approval. At number three, most effective point, we have goals of the system. Point number three. Now, for goals of the system, example in food safety include goal, minimize recalls versus the goal of produce safe food, right? The goal of pass audit versus the goal of continuous improvement safety. The goal of comply with the regulation versus the goal of protect the public health. Now, why this is high leverage? Because goals determines what system optimizes for. Different goals produce different behavior actually. Now, let's explore that with example. If goal is pass audit system optimizes for documentation and compliance theater, if goal is if goal is pass audit, system optimizes for documentation and compliance theater, right? But if goal is protect public health, system optimizes for actual safety. In the case of Period Corporation of America's implicit goal was maximize profits. So this goal drove decision to release contaminated product. Changing the goal would have changed all downstream decisions. Point number two for the most effective is mindset or paradigm out of which the system arises. Example for mindset or paradigm out of which the system optimizes in food safety include the following. Paradigm, food safety is a cost center versus the paradigm, food safety is a value center creator. The paradigm of worker are the problem versus the paradigm that workers are part of the solution. The paradigm of safety and production are in conflict, or the paradigm safety enables production. Now, why extremely high leverage this point? Because paradigm determine how people interpret information and make decisions. Example, if paradigm is workers cause problems, the response to deviation is blame and discipline the worker. But if paradigm is system conditions enable or prevent safe work, response is system redesign, as we saw earlier. So same events, different paradigm, and completely different intervention. And the most effective point, which is number one, is power to transcend paradigms. Now, why extremely this is the highest leverage point? The ability to recognize that all paradigms are limited and to shift between them as needed. This is the highest leverage point, the ability to question fundamental assumptions and reimagine the system. Example, in food safety, recognizing that the paradigm of food safety is about controlling hazard is incomplete, and shifting to food safety is about designing systems that make safe food the easy, the natural outcome. This paradigm transcends, enables the entirely new approaches, right? Now, let's explore the real world applications here, analyzing the bluebell outbreak through leverage points. The bluebell listeria outbreak of 2010 that has 10 illness and 3 deaths between 2010 and 2015 outbreak demonstrates leverage points hierarchy. Let's go through it. The low leverage point interventions. What they did, the point number 12, parameters. They had extensive testing program. That's parameters, the low leverage point. Then the point number 12, low leverage point. They had documented procedures, buffer. The, and then point number 10, structure, low leverage point. They had environmental monitoring program, structure also. Now, the result outbreak occurred despite these interventions because they targeted low leverage points. Now, the high leverage points failures, which are the root causes, are point number 6, information flow. Positive test results didn't flow to production decision maker, right? And secondly, the failure of the high leverage point number 5, which is rules. No rules requiring production stop for positive environmental results. They fail also the point number 3 goals, which is implicit goal was production continuity, not safety. And the failed point number 2, the paradigm, because the paradigm was positive environmental results are normal, not urgent in their case, right? Now, the high leverage point intervention, let's go through what would have worked if they took these high leverage points. Point number 6, restructure restructure information flow. If they had taken this, the positive results immediately to production management with the stop authority, right? The information flow. And then, if they have leveraged the point number 5 to implement the rule, the positive environment result equals automatic production halt until resource eliminated, until source eliminated. And if they had leveraged the point number 3 to change the goal, which is goals, right? From maintaining production to eliminating listeria source. And if they have leveraged the point number 2 to shift the paradigm from environmental listeria is manageable to environmental listeria is unacceptable. The leverage inside here, adding more testing from 12 parameters wouldn't have prevented the outbreak. Restructure information flow number 6 and changing goal number 3 would have. This is why understanding leveraging point is critical. It is direct efforts to high impact intervention. Let's look at the practical application, identifying leveraging point in your system. To identify leveraging points in your food safety system, do the following. Step 1, map current interventions to leverage point hierarchy. List your current food safety interventions and classify them into the following. How many targets parameters, number 12, and how many targets information flow, number 6, and how many target goal, number 3. So most organizations find 80% of effort target low leverage point from 12 to 10. Then step 2, identify high leverage opportunities. Ask these questions to identify high leverage opportunities for first for information flow. To identify high leverage opportunities there, ask who need to know what and when to make safety decisions, and what critical informations exist but doesn't reach decision making, and what information reach people who can act on it. Then rule number 3 for rule number 5, to identify high leverage opportunities, what rules would change behavior if implemented, and what current rule creates perverse incentives, and what implicit rules, unwritten norms, drive actual behaviors. Also, to find opportunity for goal, rule number 3, ask the following questions. What does the system actually optimize for? Which will be revealed by decisions under pressure, and what would change if the goal shifted, and whose goal matters, management, workers, stakeholders, or customers. And then to identify the opportunity for rule number 2, which is paradigm, ask the following questions. What fundamental assumptions drive decisions? What beliefs are unquestionable here? And what would become possible if those beliefs change? After that is step number 3, design high leverage interventions. Focus effort on leverage points from 6 to leverage to point number 2. Redesign information flow, change rules and incentives, clarify and align goals, and challenge and shift the paradigms. Step 4, use low leverage points strategically. All right. So parameters point number 12 and buffer point number 11 are still useful, but use them to support high leverage change. Don't expect them to transform system behavior, and recognize their limitations. All right. Now, Let's look at the case study. High leverage point intervention success. Let's assume a large food manufacturer experienced recurring allergen cross contact incidents despite extensive controls. Low leverage interventions. That means the extensive control is with low leverage interventions, more testing, more training, and more procedure. Well, the leverage point analysis here, the problem wasn't lack of control. That's parameter. And the problem was information flow and goals. High leverage points. The high leverage point interventions are following. Point number 6, information flow. Made allergen changeover structure visible on production flow. Digital display showing allergen changeover in progress. Do not start next production. And then the high leverage point number 5, rules. Implement the implemented rules. Next products cannot start until QA verifies changeover complete. Remove production supervision supervisor authority to override. And then the high level leverage point number 3, the goals. They change the performance metrics. Supervisors now are evaluated on zero allergen incident, not production volume anymore. The results? Allergen allergen incidents dropped from 8 years, 8 times per year to zero per year over 3 years. No increase in cost and production efficiency actually improved. Fewer disruption from incidents. Now, why it worked? Targeted high leverage points 6, 5, and 3 rather than adding more low leverage controls. Conclusion here is strategic use of leverage point. First, most efforts target low leverage point. Organizations spend 80% of resources on parameters and buffer from point 12 between point 12 and point 2, which produce minimal system change actually. Secondly, high leverage points require less efforts, such as changing information flow or changing goal, often require less resources investment than adding controls that produce transformative change, right? Thirdly, leverage points interact. Changing multiple leverage points simultaneously amplify effects. Example, changing information flow, point number 6, plus changing the rule, point number 5, plus shifting the paradigm, point number 2, equals to system transformation. 4, resistance increase with leverage. High leverage interventions face more resistance because they challenge power structure, goals, and paradigm. This resistance is a signal you have found real leverage. Fifth, start where you have influence. If you can change organizational goal, which is point number 3, start with information flow, point number 6, or rules, point number 5, with your control, then develop gradually. The fundamental insight here in complex systems where you intervened matters more than uh, hard, more than the hard you push, how hard you push, right? In complex systems where you intervene matter more than how hard you push. A small change at high leverage points produce large effects. Large effects, uh, large efforts, and large efforts at low leverage points produce minimal change. So understanding leverage points is the difference between working hard and working effectively. key reference for all that is again from the study we previewed earlier from Middle D 1999, leverage points placed to intervene in a system from Sustainability Institute. All right. Now let's discover the practical tool, the system archetypes, recognizing patterns that repeat. Certain system patterns pair repeatedly across different contexts. Recognizing these archetypes help you diagnose problems faster and design more effective solutions. All right. Now, what are system archetypes? Those are practical tools. System archetypes are common patterns of system behavior that appear across industry, organizations, and situations. Once you learn to recognize them today, you see them everywhere, including in your food safety system. The key archetypes in food safety: number one, fixed uh, fixes that fail. Pattern here: a solution provides immediate relief but creates unintended consequences that make the problem worse over time. The food safety example for that problem: positive environmental test results. The quick fix: increased cleaning frequency. Unintended consequence there: the staff becoming fatigued and cleaning quality decrease. So the long-term result there: more positive despite more cleaning also, right? Because the cleaning quality now decreased and the staff becoming fatigued. The better approach here is understanding why contamination occur, redesign to prevent it rather than just cleaning more. Okay. Second type of archetype is shifting the burden. The second the pattern here: a symptomatic solution is used repeatedly, preventing implementation of a fundamental solution. And over time, capability to implement the fundamental solution weakens. In food safety example, fundamental solution: fix equipment designed that harbor contamination. The symptomatic solution here: increased testing and cleaning. The result: organizational become dependent on testing and cleaning, never fix the equipment. The problem persists here because the fundamental problem remains unaddressed. So the better approach here: invest in fundamental solutions even when symptomatic solutions seem easy. Third archetype: eroding goals. The pattern here is when performance falls short of goals, instead of improving performance, goals are lowered. This creates a reinforcing loop of declining standards. Let's explore the example in food safety. The original goal, let's assume, is zero environmental positive, but the performance, 5 positive per month. The response: adjust goal to acceptable positive. And the results here: positive increase to new acceptable level and the goal lowered again. The better approach would be maintain standards, improve capability to meet them there, right? Other archetype is success to the successful. The pattern here: resources flow to whoever is currently successful, creating a reinforcing loop that starves struggling areas of resources they need to improve. Let's demonstrate with example here in food safety. The high performance facility gets more investment, more recognition, and more resources. The struggling facility gets criticism reduced resources, and less support. The results here: gap widens, a struggling facility falls further behind. And the pattern here: success breeds success and struggle breeds failure. The better approach here will be invest strategically in struggling areas to break the cycle. Fifth archetype: tragedy of the common. The pattern here: when multiple parties share a common resources, individual optimizations lead to collective depletion. Let's explain. In food safety example, the standard resource here, the shared resource, is equipment between production lines. Okay, and the individual optimization here, each line minimizes downtime. The results: insufficient time for proper cleaning between uses. The pattern here: individual optimization creates collective risk. The better approach here: manage shared resources with system level optimization. All right. So, how to use the archetypes? First, recognize the pattern. When facing persistent problems, ask: does this match a known archetype? Then, understand the structure. Identify the feedback loops and delay that creates the problem. Then, find the leverage point. Each archetype has characteristic leverage point where intervention is most effective. Then, design the solution. Use the archetype's structure to design solutions that address root causes, not symptoms. Practical exercise here. Review your three most persistent food safety challenges. For each challenge, ask the following: does this match an archetype? What feedback loops are creating this pattern? Where is the leverage point here? And what fundamental solutions would break the pattern? Now let's do the connection to module 3 here. In module 3, the 5 failure patterns, those are the most important patterns, by the way. You should check them out. The, the 5 failure patterns are themselves archetypes. Pattern 1 is slow failure, equals the eroding goal archetype here. The pattern 3, problem moves forward, equals to shifting the burden archetype here. And pattern 4, symbolic evidence, equal to fixes that fail archetype here. And then the pattern 5, pressure wins, equals to tragedy of the common archetype. These will prepare you for rapid diagnosis of system problems that we will address as we progress through, designing solutions that address structure, not symptoms, and avoiding common traps in system design, and recognizing when your solutions might create new problems. Now, let's explore the importance for credibility. Why more rules make things worse, right? The instinctive response to problems. When problems occur, the reflexive response is often the following: write more procedures, add more checks, increase documentation requirements, create more approval steps, and implement more trainings. This feels like strengthening control, but more rules equals to more controls that equals to more safety. That's the instinctive we have, right? Well, why this logic fail? In complex systems, more rules often create less control. So this is, and we are going to explore now, and this is not because the rules are bad, it is because excessive rules create unintended consequences. First, the complexity breeds shortcuts. So when procedures become too complex to follow consistently, people create shortcuts. The workarounds become standards practices, and the original rules become symbolic. Also, the focus shifts to compliance. Energy that should go to actual safety instead goes to maintaining documentation, satisfying audit, and proving compliance. And then also people adapt to service to survive. Okay, so when rules make work impossible, people find ways around them. The system trains people to circumvent controls rather than strengthen the safety. And then judgment is discouraged. There, excessive rules tells people don't think, just follow the procedure. But food safety requires judgment, adaptation, and thinking. The evidence here, multiple outbreaks investigations reveal that facilities with extensive procedures still experience catastrophic failures, not because they lacked rules, but because of the following. First, rules were too complex to follow under operational pressure. People focus on documentation rather than actual controls. Workaround becomes normalized, and critical judgment was replaced by procedure follows. Now, research on regulatory burden and safety outcomes consistently show no direct correlation between the sheer number of procedures and improved safety performance. For instance, studies published in Journal of Food Safety in 2020 indicates that facilities with over 500 pages of procedures often have similar incident rates to those with fewer than 100 pages, suggesting that complexity does not equal to safety. Now, another notable example in the 2009 PCA or Peanut Corporation of America salmonella outbreak investigation revealed that while the company had extensive documentation, they focus on paperwork and culture of cutting corners to meet production demands, diverted attention from actual contamination issues. The complex documentation requirements effectively masked critical failure in practical food safety management, rather than preventing them. The better approach would be design design over enforcement. Simplicity as strengths. Instead of more rules, make the right things the easy thing. Instead of more procedures, design systems that work intuitively. Instead of more checks, build verification into workflow. And instead of more training, make mistakes impossible or obvious. Example of design uh, over rules here. Uh, First, the rule heavy approach, 23-page cleaning procedure, 17 sign off requires, quarterly training on procedure, and monthly audit of compliance. The results here people create shortcuts because procedure is too complex. Now, the design focus approach would be equipment designed for easy cleaning, color coding prevents cross use, timer prevents shortcuts, visual indicators show completion, and the result here is doing it right is easier than doing it wrong. All right, let's explore this case study of simplifications at Safe Harvest Food. A leading organic produce processor, Safe Harvest Food, was struggling with rising incident rates despite having hundreds of pages of procedures. Recognizing the burden, they launched an intuitive an initiative to streamline their food safety management system. So they engage frontline workers to identify redundancies and bottlenecks, consolidating over 300 pages of SOPs into a concise, visual driven manual of less than 70 pages. So they invested in automation and equipment upgrade to simplify critical tasks. Within 2 years, Safe Harvest Food reported a 45% reduction in m- minor nonconformance and 20% improvement in audit score, proving that simplification, when done strategically, lead to tangible safety improvements. The distinction here, this is not saying that have no rules or standards don't matter. Standards are essential. The point is simple, well designed systems are stronger than complex, rule heavy systems. Design that makes mistakes impossible is better than procedures that requires perfection. Verification that built into workflow is more reliable than separate checklist. Okay. Now, this is this perspective align with the safety 2 and resilient engineering principles, which emphasize understanding work as done, how tasks are actually performed, rather than just work as imagined, like how procedures describe the way they should be done. Real safety comes from the ability of a system to adapt and recover, not just from adherence to an exhaustive rule book. The practical diagnostic here, count your food safety procedures page. Okay, if the total is over 200, you likely have a level of complexity that is creating workarounds and diverting attention from actual risk. This is a strong indicator that simplification efforts could yield significant safety benefits. This supports design over enforcement as a principle, simplicity as a strength, building intelligence into system structure, and focusing on effectiveness, not just compliance. Now, let's discover the trust repair here. People are system elements moving beyond the human error paradigms. Okay? The traditional framing and its consequences is the following. The dominant paradigm in food safety treats people as the weak link, unreliable system components that cause failure through human error. This paradigm, inherited from early 20th century industrial engineering, fundamentally misunderstands how humans function within complex systems. Okay? Research in human factors, safety science, and organizational psychology demonstrates that people are not defective system components. They are adaptive agents whose behavior emerges from system conditions. This distinction is not semantic again, it uh, determines whether interventions address uh, symptoms like blame and retrain or root causes like redesign the system conditions as we explore throughout this module. The human error paradigm, let's discuss that. The structure and limitations here. When food safety failure occur, investigations typically concludes the following. Workers fail to follow the procedure, operator error caused contamination, Employee didn't wash hands properly, and staff took shortcut. This framing assumes the following. First, procedures are correct and feasible. Secondly, workers choose to violate procedures. And thirdly, training and discipline will prevent recurrence. And fourth, the system is fine and people are the problem. Those are the assumptions. Now, why this paradigm fails? We have research by Sidney Decker, The Field Guide to Understanding Human Error, 2014, and James Reasons, The Human Error, publication in 1990, demonstrate that human error is not a cause. It is a symptom of system conditions that make errors likely or inevitable. All right? And the evidence for that are the following. 70 to 80% of food safety incidents are attributed to human error. FDA inspection data, according to FDA inspection data, yet retraining and discipline rarely prevent recurrence. So, same errors occur repeatedly across different people. The errors increase under predictable conditions, time pressure, understaffing, and equipment problems. These patterns indicate system level causation, not individual failure. We all agree on that, right? Now, let's explore the real world case study, the Peanut Corporation of America outbreak that we have been studying so far. The 2008 to 2009 salmonella outbreak, which resulted in 9 deaths and 714 illnesses, is often framed as management deliberately released contaminated product, a human error of bad or the bad actors narrative, right? Now, human factor analysis reveals system causation here. The behavior, the product tested positive for salmonella. Secondly, instead of investigating, product was retested. Thirdly, the retesting continued until negative results obtained, and the product released based on negative results. All right. Now, the traditional framing here would be management made an ethical decision to release contaminated product, right? Well, the system analysis would say what system conditions made this rationale. Okay, instead of you remember that's how we start our model today. So we will start the investigation like this. What system conditions made this behavior rational from the actor's perspective, right? The system condition number one is economic pressure. All right. The economic pressure include the following. First, the company operating on thin margin. That's the fact. And then the holding products equals the financial loss also. That's a fact. And then no buffer to observe costs of investigation also. And then the system condition now we can conclude that economic structure made holding product financially threatening. Correct? Secondly, let's look at the system conditions number two, the regulatory gap here. First, no requirement for environmental monitoring at the time, and no requirement to investigate positive results at the time, and there was no prohibition on retesting until negative, and there was no system conditions. The regulatory structure allowed the behavior. That's system condition number two, regulatory gap. Let's look at the system condition number three, information asymmetry. Okay. First, the management knew test results. Secondly, customer didn't know test results. Thirdly, no transparency requirements there. And fourth, system conditions there, information structure enabled the concealment, right? The transparency requirement was not there. Now, the fourth condition, system condition here is delayed feedback. First, the contamination product was shipped. Secondly, illness occurred weeks or months later. Fourth, no immediate consequences visible to decision makers. And fifth, the system condition here, no, the system condition here for the delayed feedback delayed broke the connection between action and consequence. Now, the insight is the behavior wasn't irrational or purely unethical. It was a predictable response to system condition that allowed the following. First, made holding product financially threatening. Secondly, allowed retesting without investigation. Thirdly, enabled information concealment. And fourth, it allows delays consequences beyond decision horizon. Now, the implication here, blaming bad management misses the point. Okay, the different managers in the same system conditions would face the same pressure and incentives. So, preventing resources requires changing system conditions, not just replacing people. Okay, preventing recurrences requires changing systems, not just people's. Now, let's explore the theoretical framework here. People as adaptive agent. All right. Now, modern food science, and particularly the work of Eric Hollingale, the Safety 1 and Safety 2 2014 publication, and the resilient engineering community recognizing, reconceptualize the human role in the system here. First, people are not the following, not detective components that need fixing. People are not unreliable elements that need controlling, and people are not sources of error that need eliminating. People are the following, adaptive agents who adjust behaviors to local conditions, sense makers who interpret ambiguous situations, and problem solvers who work around system limitations and the source of system resilience, not just failure. Okay. Now, the key concepts here. One, work as emergent versus work as done. Work as emergent, how procedures describe work, and work as done, how work actually happen. That exists because procedures cannot anticipate all conditions. Okay. Wor- Workers adapt to bridge the gap. This adaptation is necessary for system function, actually. Okay. Example in food safety. The procedure here, clean equipment after each production run. All right. The reality is equipment breakdown delays production, schedule is compressed, and cleaning time is reduced. Now, work as done here, workers prioritize critical cleaning step. Deferred, yes, critical step, right? They just took the critical step and go with it. This is not violation, it is adaptation to system conditions, the equipment reliability, and schedule pressure. Secondly, let's look at the performance variability here. Human performs varies based on context. Human performance varies based on context, and variability is not defect, it is adaptation. Same variability that cause occasional failure enables routine success, for example. Okay? You cannot eliminate variability without eliminating adaptability. Example in food safety. Worker noticed unusual odor during production. Bad smell. Okay? Then the production doesn't specify, the procedure doesn't specify to stop work for unusual odor or unusual smell. Now, The worker uses judgment to stop lying and investigate. This variability, the judgment, prevents contamination. The same variability might occasionally cause unnecessary stops, but eliminating judgment, strict procedure compliance would eliminate this protective adaptation. Well, now let's look at system conditions shapes behavior. First, behavior emerge from interaction of person and system conditions. Secondly, same person behaves differently in different system conditions. Third, different people behave similarly in same system condition. Okay? Fourth, changing behaviors requires changing system condition. Let me explain that with example in food safety. Adequate staffing will lead to workers follow the full procedure. Now, under staffing, workers will take shortcuts to maintain production. So you have the same workers, different system conditions, and different behavior. Okay. Application here to the standards 2022, ISO 2018, recognizing human factors through uh, though incompletely, the ISO 22000 recognizing human factors. In clause 7.2, the competence requires ensuring persons are competent based on education, training, and experience. This addresses individual capability but not system conditions that enable or constrain performance. And also in class 7.3, the awareness requires persons to be aware of food safety policy, their contributions to food safety management system effectiveness, and implications of not conforming. This address knowledge but not system pressure that drive behavior. Also in clause 7.4, the communication. It requires communication to enable personnel to address their role, to understand their roles. This addresses information but not system condition, time pressure, and the resources constraint and the conflicting priorities that shapes behavior. So what's missing here? First, recognition that behavior emerged from system condition, and also requirement to analyze system conditions that make errors likely, and also requirements to design system that makes safety behavior that safe behavior the easy and natural choice, and also recognition that people are source of resilience and not just failure. That's what's missing. The gaps, ISO 22000, treat people as elements to be trained and made aware, not as adaptive agents who behavior emerge from system conditions. This perpetuates the human error paradigm. The practical framework here, system condition analysis. When human errors occur, analyze system conditions instead of blaming individuals. Okay. Step one, describe behavior without judgment. First, not workers failed to follow the procedure. Instead, worker cleaned equipment for 10 minutes instead of specified 20 minutes. Step two, understand behavior from actor's perspective. Ask what made this behavior make sense to the person at the time. What information did they have? What pressure were they under? What constraint did they have? And what goals were they trying to achieve? Okay. Step three, Identify system conditions. What system conditions shape the behavior? If it's time pressure, production schedule, was production schedule compressed? Was there understaffing? Was there equipment breakdown created the backlog? If it is resources constrained, are there adequate cleaning suppliers available? Are equipment functioning properly? Are staffing personnel? Are there sufficient personnel? If it's of information availability, did workers know why 20 minutes required? Was there feedback on cleaning effectiveness or consequences of inadequate cleaning visible? If it's conflicting goals, pressure to maintain products uh, versus thorough cleaning, supervisor emphasizes on speed versus quality, and performance metrics reward production volumes. If it's a procedure feasibility, is 20-minute cleaning time realistic given equipment design? Does procedure account for actual work conditions? Was procedure designed with workers' input? Then step 4, redesign system condition. Change conditions that make error likely. If time pressure, adjust production schedule to allow adequate cleaning time. Add staff during high volume periods. Improve equipment reliability to prevent delays. If resources constraints, ensure suppliers always available, maintain equipment properly, and adequate staffing level. If information gaps, explain why 20 minutes requirement. Okay, microbial reduction kinetics. Okay, for example, and provide feedback. ATP monitoring shows cleaning effectiveness. Use ATP, right? And then make consequences also visible. Environmental monitoring results. If it's conflicting goals, align performance metrics with safety. Reward through cleaning, not just speed. Supervisor training on balancing production and safety, and also authority to stop production when safety is at risk. If procedure infeasible, redesign procedure with worker input, modify equipment to enable effective cleaning, validate that procedure achieve intended outcome. All right, now let's look at the case study. The system redesign success. Poultry processor experienced recurring salmonella contamination attributed to workers not following sanitation procedure. All right. The traditional response, which failed, is the following: retrain workers 3 times, discipline workers for violation, increase supervision, and the results: contamination continued. Well, the system analysis investigated the system conditions as following: sanitation shift 11 to 7 a.m., night shift. Staffing chronically understaffed, high turnover, time pressure, must complete sanitation before 7 a.m. production start. Equipment, aging equipment with hard to clean areas. Feedback, no immediate feedback on sanitation effectiveness. Now, the system redesign will follow as this. First, extended sanitation time. Production start move to 8 a.m. Okay, to remove the time pressure there. Secondly, improve staffing, increase wages, better working condition. Thirdly, replace aging equipment with cleanable design. Fourth, implement ATP monitoring, immediate feedback. And fifth, change metrics. Supervisors evaluated on sanitation effectiveness, not completion time anymore. As a result, salmonella environment positive drop from 15, environmental positive dropped from 15% to 2%. Worker turnover decreased, no additional training required, and behavior changed because system conditions changed. The insight here, workers weren't the problem, system condition were. Changing conditions change behavior more effectively than training and discipline. All right. Conclusion here, the paradigm shift. Moving beyond the human error paradigm requires recognition. First, behavior emerged from system conditions. People adapt to the conditions they face. Change conditions and it will change the behavior. Secondly, error is a symptom, not a cause. When errors occur, ask what system conditions made these errors likely or inevitable. Thirdly, people are source of resilience. Workers adapt to system variability. Workers uh, work around limitations and prevent failure daily. This adaptability is essential. Don't eliminate it by over procedurizing. Fourth, blame prevents learning. Blaming individuals stops investigation at the person. Missing system levels causes. No blame culture enables deeper analysis. Fifth, system redesign beats retraining. Training addresses knowledge. System redesign addresses conditions. Most errors occur despite adequate knowledge, because system conditions make errors likely. Now, the fundamental shift here, error shift from error to we fix people from how to. The fundamental shift here is from how do we fix people to how do we design system where safety behavior is the easy natural choice. All right. This is not about um, excusing poor performance. This is about understanding that sustainable improvement comes from system redesign and not individual blame. Now, using the key references here from Decker S. 2014, The Field Guide to Understanding Human Error, the third edition, and also the Hellengale E in 2014, Safety 1 and Safety 2, The Past and the Future of Safety Management. And then also from Reasons J, 1990, Human Error in Cambridge University Press. Now, let's explore the implementation guide here. Applying system thinking, a practical framework. System thinking isn't just theory, it's a practical approach you can apply immediately. Here is how to use system thinking to analyze and improve your food safety system. Use this 5-question framework to implement system thinking. First question, what's the pattern? Don't just look at individual incidents, look for patterns. Does this problem repeat? Where else does it occur? When does it occur? What conditions are present when it occurs? Example, instead of we had a temperature deviation, ask, we have had 12 temperature deviations in 12 months. What patterns connects them? Right? That's the first question. What's the pattern? Second question, what's the structure? Identify the system elements and interconnections. A, what elements are involved, such as equipment, people? procedure, or information? B. How do they connect? C. What feedback loops exist? D. Where are the boundaries? E. What delays are present? Example here, temperature deviation occur during shift change. That's a boundary. When production pressure is high, that's interconnection, and are not detected until the next day, the delay. Third question, what's the behavior over time? Look at the trends, okay? Look at trends, not just snapshots. First, ask, is this getting better or worse? Then, how fast is it changing? Then, what's the trajectory? Then, are we in a reinforcing or balancing loop here? Example, temperature deviation started at 1 per month. Now 2 per month, 2 deviation per month. Reinforcing loop of declining performance is what you can see here. Thirdly, the fourth question, what is the leverage? Identify high impact intervention point. First, where does a small change create large effects? Secondly, what's what's preventing the system from self-correction or correcting? Then, where's the feedback fastest? Then, where is authority clearest? Example, the leverage point isn't more training. It is fixing the shift handover process where information gets lost. The fifth question, what's the intervention? Design solutions that address the structure. How do we change the interconnection? How do we speed up feedback? How do we break reinforcing loops driving decline? How do we create reinforcing loops driving improvement? Example here, implement real-time temperature alert, fast feedback, plus clear handover protocol, fix interconnections, plus shift overlaps to eliminate the boundary. The practical application, first step, map the current system for 30 minutes. List key elements, draw connections between them, identify feedback loops, and note delay and boundaries. Step 2, identify pattern, patterns for 20 minutes, review incident data for patterns, look for recurring problems, identify systems archetypes, and connect to Module 3 patterns. Step 3, find leverage points. 20 minutes. Where is feedback broken or slow? Where are boundaries creating blindness here? Where are where are reinforcing loops driving declines here? Where could a small change have large effects here? Step 4, design intervention. 30 minutes. Focus on its structure, not symptoms. Address interconnections, not just elements. Speed up feedback loops and simplify where possible. Step 5, test and learn. And this is an ongoing. Implement a small change, monitor system response, adjust based on feedback, and scale where what works. The common mistake here to avoid, first mistake, jumping to solutions. Don't skip the analysis, understand the system before interventing. Mistake two, focus focusing only on elements. Adding more controls without fixing interconnections doesn't work. Third mistake, ignoring delay solutions. No, ignoring delays. Solutions that don't account for delay will fail. Fourth mistake, treating symptoms. Quick fixes that don't address the structure create new problems. Fifth mistake, expecting immediate results. System change take time. Monitor trends and not snapshots. The success indicators here, ask what patterns before what happened. Look for interconnections, not just causes. Consider delay between actions and consequences. Identify leverage points before adding controls. Design for feedback, not just compliance. See people as part of the system, not the problem, and focus on structure, not blame. Your next step, choose one persistent problem in your food safety system. Apply the 5 questions framework above. Here they are again. What what's the pattern? What's the structure? The explanation are above there. What's the behavior over time? What's the leverage? And what's the interventions? Document your analysis, share it with your team, test your interventions, and learn from results. This prepares you for Module 5. Module 5 will teach you to design food safety system from the ground up using system thinking principles. You will learn to design for feedback, not just control, build in resilience, not just compliance, create systems that learn and adapt, prevent the 5 failure patterns. You now have the lens. Module 5 will give you the blueprint. Essential closing. Module 4 closing reflections. As we conclude this module, we offer we offer not an action question here, but a profound seeing question to shift your perspective. The question is this: where in your food system are perceived human error actually brilliant adaptation to systematic design flow or organizational pressure? The question again: where in your food system are perceived human errors actually brilliant adaptation to systematic design flow, or organizational pressure? This is a question for you to see clearly and to shift your perspective. Now, why this question matter? This question makes invisible systematic risk visible. It compels you to examine your system with new, critical eyes, moving beyond superficial blame. Example of relying on people to compensate for weak design. First, cleaning procedures that require perfect execution because equipment is hard to clean. Secondly, monitoring systems that depend on someone remembering to check and respond. Thirdly, interface management that relies on people to verbally communicate critical information. Fourth, controls that work only if people are fresh, alert, and unhurried. Then, safety system that depend on people speaking up on cultures that punish bad news. The key takeaways here from Module 4: people are part of the system. Human performance is a resource for safety, not just a liability. Behavior is rational adaptation. People adapt to make work happen, often responding to incentive and systematic pressure. Error as a symptom, many incidents attributed to human errors are symptoms of deeper system design flaws. Now, how to answer honestly? Walk through your operation and ask at each step the following questions. What happens if someone is tired, rushed, or distracted? What happens if someone forgets one step? What happens if information doesn't transfer verbally? What happens if someone doesn't speak up about a concern? If the answer is catastrophic failure, you are relying on people to compensate for weak design. This question is designed to make design flaws visible that were previously invisible, shift focus from blaming people to fix systems, create productive discomfort without defensiveness, prepare for Module 5, where prevention design becomes the focus. The immediate next step, identify one area in your daily routine where you notice someone consistently making an extra effort to overcome a system limitation. Simply observe it without a judgment, right? But do not provide immediate answers or solutions or tell people how to fix what they identify or turn these into an action plan. The significant problems we have cannot be solved at the same level of thinking we use we use when we created them. That Mr. Albert Einstein. Let the discomfort sit. Let the question work. This system thinking perspective empowers you to not just solve problems, but to design for resilience and enhanced safety. Module 5 will provide the tool for proactive provision design, prevention design. Sorry. Now, the transition to Module 5 from insight to impactful design. Module 4 challenge your perception, revealing that food safety is not about just about compliance, but about dynamic system behavior. Now, we move beyond understanding the how things go wrong, actively engineering systems that make them go right. Prevention isn't assumed here, it is meticulously designed. From observation to action, your Module 4 foundation. You have gained critical insight into the living, interconnected nature of your food system. Here's how those discoveries empower your design work. You now see system thinking provides a clear lens, analyze interconnections and outcomes, allowing you to design with holistic perspective. You recognize that linear approaches fail in dynamic environments, preparing you to build flexible and adaptive design. You understand food safety as a living system, ready to design mechanisms for ready to design the mechanism for it to sense, respond, adapt, and learn automatically. You have observed how hazard grow, speed, and transforms, enabling you to design proactive interpretations, interruptions to their flow. You have identified boundaries and their blind spots, informing your approach to create more integrated and transparent design. You appreciate the power of feedback loops, and you are now equipped to design systems that continuously learn and improve. You have unmasked how delay obscures cause and effects, guiding you to design for clearer, more immediate indications or indicators. You have pinpointed leverage points, giving you the ability to make a small, targeted change for significant positive efforts. You have recognized that more rules often weaken systems, leading you to design for inherent safety rather than over regulations. You now view people as essential parts of the system, not problems, paving the way for human centric design. The critical shift in Module 5, designing for inherent safety. Module 5 marks a profound shift from passive observation to active creating. We will reframe prevention and HACCP not as rigid documentation, but as powerful design logic. You will learn the following. You will learn to engineer resilience, design systems that inherently interrupt failure patterns even under pressure. You will learn to build robust controls, creating safety measures that function effectively in real world, messy conditions. You will learn active continuous learning. You learn to activate continuous learning to develop feedback loops that transform incidents into opportunities for system growth. You will learn to optimize interactions, to manage interfaces explicitly, ensuring seamless information transfer and collaborations. You will learn to empower your team, to design systems that support and elevate human performance rather than fighting against it. The promise, it will transform your system, transform your Module 4 gave you new eye to see your system's hidden dynamics. Module 5 will equip you with the practical tool and strategic mindset to not just understand, but to actively redesign it for unparalleled safety and efficiency. If system thinking reveals how food safety fails, prevention design empowers you to master how to make it succeed. Module 4 summary. Module 4 from blind spot to systematic insight. We have completed Module 4 now, and your understanding of food safety has fundamentally shifted. You no longer see isolated events, but interconnected systems. It transforms perspective. What's different now? Before, we have static and linear. You saw hazards on lists, controls at fixed point, and problems as isolated incidents, people as potential failure, and documentation as proof of control. That's what you see before, right? Now, you see dynamic and interconnected. You see hazards as flow through the systems, controls as part of the feedback loops, problems as symptoms of design, and people as integral parts of adaptive systems, and documentation as tools for system sensing. Your next, your new systematic capabilities now, flow analysis. You can now trace how hazards grow, spread, and transform within your system, enabling proactive interruption. And then feedback mastery. You understand controls as essential feedback loops, equipped to design systems that continuously learn and improve. Problem redefinition. You recognize problems not as isolated failure, but as emergent symptoms of underlying system design issues. Human centric view. You view people as vital system components, not problems, paving the way for human centric safety design. Leverage point identification. You can pinpoint small targeted change for significant positive effects across entire system. You know you have you, you know you are thinking systematically now when instead of is this hazard controlled, you ask how does this hazard flow through my system? You consider how does my system sense problems and how fast does feedback return? You look for where do boundaries create blind spot or where am I relying on people to compensate for design? You identify what leverage points would create the largest, most sustainable improvement. Your assignment before Module 5 now, answer closing question for your operation. Where in your food system are you relying on people to compensate for weak design? Identify, list 3 examples for each node. What weak design requires people to compensate? What happens when people can or don't compensate? What system redesign would eliminate the need for compensation? You have gained new eyes to see your organization's hidden dynamics. Module 5 is not just about applying these insights, it is about actively engineering them into resilient, adaptive prevention systems. Prepare to move from understanding to truly impactful design. Thank you and see you in Module 5.